Hello there and welcome to Science for Sleep, where we take some of the biggest questions in science, slow them down a little, and explore them without requiring anyone to sit an exam at the end. Tonight, we're going back almost as far as Earth itself, not to the age of dinosaurs, not to the first oceans, the first continents, or even the first living cells. We're going much farther back than that, to a time when our planet was still young, extremely hot, frequently struck by large objects, and generally having the sort of childhood that would make modern Earth look remarkably well adjusted. And somewhere in that violent early solar system, another world was moving around the sun. We call it Theia. You won't find Theia in the night sky. There is no photograph of it, no telescope image, and no ancient rock with a convenient label saying, "Property of Theia. Please return if found." The planet itself disappeared billions of years ago. But according to the leading explanation for the origin of our moon, Theia may have disappeared because it collided with Earth. And part of it may still be here. Some of it may be in the moon. Some of it may have mixed into Earth. There is even research investigating whether pieces of Theia's mantle could have survived deep inside our planet, far beneath our feet, for billions of years, which is an unusual fate for a planet. Most planets, if everything goes reasonably well, get to remain planets. They orbit their star, collect a few craters, develop weather if they're lucky, and generally keep their own name. Theia apparently had other plans, or rather gravity had other plans for Theia. Tonight, we're going to follow the evidence for one of the most important collisions in the history of our planet. A collision so enormous that it may have transformed Earth, destroyed another planetary body, surrounded our world with hot debris, and eventually produced the moon that now hangs quietly in our night sky. And before we go any further, I'd love to know where you're listening from tonight. Perhaps the moon is outside your window right now. Maybe it's full and bright enough to throw shadows across the ground. Maybe it's a thin crescent sitting low over the rooftops. Maybe it's hidden by clouds. Or perhaps you're listening during the day, in which case the moon may still be somewhere above you, simply being rather difficult to spot. Wherever you are, take a moment to think about something slightly strange. That object in the sky may exist because Earth was once hit by another planet. Not a small asteroid, not a comet, a planetary body. Something large enough to have its own interior, its own history, and perhaps its own path toward becoming a permanent member of the solar system. Instead, it encountered Earth. And after that encounter, neither world was quite the same. If you find these quiet journeys through science relaxing, interesting, or simply useful company while you're settling down, you can give the video a like and subscribe to Science for Sleep. It helps more people find this little corner of science, particularly those who enjoy learning about planetary collisions while attempting to do absolutely nothing more demanding than remain horizontal. And with that taken care of, get comfortable. There is a lot of time to cover. About 4.5 billion years of it. The moon feels permanent to us. Human beings have never known an Earth without it. Long before anyone understood what the moon was, people watched it move through the sky. They used its changing appearance to mark time. They built calendars around it. They told stories about it. They navigated by its light. They noticed that the oceans rose and fell in a rhythm connected to its position. Eventually we sent machines there. Then people, astronauts, walked across its surface, collected rocks, took photographs, left equipment behind, and returned to Earth carrying pieces of another world in sealed containers. Those rocks turned out to be far more than souvenirs. They became evidence. Because once scientists began studying lunar material carefully, they encountered a problem. Earth and the moon appeared to be closely related. Very closely related. In several important isotopic measurements, lunar rocks and rocks from Earth's mantle are remarkably similar. That similarity became one of the central puzzles in the story of lunar formation. If the moon had simply formed somewhere else in the solar system, and later been captured by Earth's gravity, why should its material resemble Earth so closely? If Earth had somehow spun so quickly that a piece of the planet broke away, how would that process actually work? If Earth and the moon simply formed side by side from the same region of material, could that explain their masses, their motion, and the amount of angular momentum in the Earth-Moon system. For a long time, scientists explored several possibilities. None of them explained everything particularly well. Then another idea moved to the centre of the discussion. Perhaps the Moon was born from an impact. Picture Earth when it was young. It was not the familiar blue planet shown in satellite photographs. There were no green continents, no forests, no birds, no whales, no cities. No one was standing around complaining about the weather, because there was no one to complain, and the weather itself would have been the least of your problems. The young Earth was still assembling. Material left over from the formation of the solar system continued to strike growing planets. Some collisions involved small debris. Others involved enormous planetary embryos, bodies that had grown from dust, rock, and metal into objects hundreds or thousands of kilometers across. The early solar system was not a neat arrangement of 8 mature planets, politely remaining in their assigned lanes. It was crowded. Objects interacted gravitationally. Orbits shifted. Bodies collided. Some merged, some shattered. Some were thrown toward the sun. Others were thrown out into distant regions. Planet formation was not simply a matter of small balls gradually becoming larger balls, while everything remained calm. It was messy. If you've ever tried to organise a drawer by tipping the entire contents onto the floor first, imagine doing something vaguely similar with several trillion tons of rock moving at planetary speeds. Although, to be fair to the solar system, it did eventually produce a fairly respectable arrangement. Earth was one of the worlds growing in this environment, and so was the object we now call Theia. The name comes from Greek mythology. Theia was a titan associated with light, and the mother of Selene, the goddess of the moon. It's a fitting name, although the object itself would not have known that. There was no little sign floating above it saying Theia. The name was applied much later by humans trying to discuss a planet that no longer exists as a separate world. Even calling Theia a planet can require a little care. Depending on the model being discussed, scientists may describe it as a protoplanet, a planetary embryo, or an impactor. In the traditional version of the giant impact hypothesis, it is often imagined as roughly Mars-sized, but Theia is not an object whose exact dimensions we have measured. We are reconstructing it. That distinction matters. We know the moon exists. We can measure the moon. We can study its rocks. We can map its gravity. We can examine its craters. Theia is different. Theia is inferred from what happened afterward. It's a little like arriving in your kitchen in the morning and finding a broken plate. A chair moved across the room, flour on the ceiling, and a very guilty-looking cat. You did not witness the event, but something clearly happened. Planetary science works with considerably better evidence than the expression on a cat's face, but the principle is useful. Scientists examine what survived. They compare chemical compositions. They measure isotopes. They calculate orbital dynamics. They build computer simulations. They ask how Earth and the Moon could have ended up with the properties they have today. Then they work backward. Theia emerges from that reconstruction. Somewhere during Earth's early history, according to the giant impact idea, the trajectories of these two growing worlds crossed. The collision was not like two solid billiard balls tapping each other. At planetary scales and impact velocities, rock behaves in ways that are difficult to picture from everyday experience. Enormous pressures develop, temperatures soar, rock melts. Some material can vaporize, mantles deform, metallic cores interact, material can be thrown into orbit. A planet can stop being a recognizable planet in an astonishingly short period of time, and that is probably what happened to Theia. Depending on the particular model, the impact may have been somewhat glancing rather than perfectly head-on. The geometry matters because it affects how much material escapes, where that material comes from, how quickly Earth rotates afterward, and how the debris eventually produces a moon. Scientists continue to test different versions of the event. There isn't one universally accepted movie of the impact that we can simply press play on and say, yes, that's exactly what happened. Instead, there is a family of models, Some involve a Mars-sized Theia striking a larger proto-Earth. Some explore impacts with different masses and speeds. Some produce an extremely hot structure in which vaporized rock surrounds a rapidly rotating inner region. Some attempt to explain why Earth and the Moon are so isotopically similar by allowing extensive mixing after the impact. Others investigate whether Theia itself formed from material chemically similar to the material that made Earth. This is one of the things that makes the story so interesting. The basic idea sounds simple. A planet hit Earth and helped create the Moon. Then you look closely and discover that nearly every word in that sentence opens another scientific question. What kind of planet? How large was it? Where did it form? What was it made of? At what angle did it hit? How fast was it moving? How much of Theia ended up in Earth? How much ended up in the Moon? How much escaped entirely? Did its metallic core merge with Earth's core? Did its mantle mix completely with Earth's mantle? Could parts of that mantle still exist deep underground today? And perhaps the most obvious question of all, if the impact was so destructive, how did a moon emerge from it? The answer involves material that did not immediately fall back to Earth. After the collision, a vast amount of hot rock would have occupied the space around our planet. Some of it was molten, some may have been vaporized. The exact state depends on the impact model. This material began interacting through gravity. Particles and blobs collided. Material exchanged energy. Some fell back, some remained in orbit. Over time, enough orbiting material gathered together to form a new body. The Moon. That sentence makes the process sound pleasantly organized. It was not. You should not imagine a few rocks gently gathering in orbit like people taking their seats before a quiet lecture. The environment immediately after a moon-forming impact would have been extraordinarily energetic. Earth itself was deeply altered. Its outer layers were heated. Its rotation may have changed. Its material was mixed with material from the impactor. Above it, the future moon was beginning as debris. The moon we know today, cold enough for astronauts to walk across and quiet enough that footprints can remain undisturbed for extremely long periods, began in heat and violence, and Theia vanished into that process. This is where the story becomes more than an explanation for why Earth has a large moon. Because if Theia contributed substantial material to Earth, then the planet you're living on is not simply the original Earth, continuing unchanged from its formation. Modern Earth may be partly Theia. Every mountain, ocean basin, continent, and person exists on a world that was rebuilt after that collision. The atoms involved have been mixed, recycled, melted, buried, erupted, weathered, and moved around for billions of years. Nothing about you is going to suddenly announce itself as a piece of an ancient planet, of course. Your left elbow is not likely to turn out to be Theian, but on a planetary scale, the question of how much material came from the impactor is serious. One recent line of research has even examined enormous structures deep in Earth's mantle, called large, low-velocity provinces. There are two especially large regions near the boundary between the mantle and the core, one beneath Africa and another beneath the Pacific. Seismic waves travel through them differently from surrounding mantle material. Scientists have debated what these regions are and how they formed. A 2023 study explored the possibility that dense material from Theia's mantle survived the collision, sank through Earth, accumulated near the core, and remained there through much of our planet's history. It's a fascinating possibility. It is not the same thing as opening a cupboard and discovering Theia sitting behind the cereal. The structures are real. Their interpretation as surviving Theian material is a hypothesis being tested. But if that interpretation eventually proves correct, then the planet that made the moon did not completely disappear. Part of it may be sitting thousands of kilometers below us. That would mean we're living on the result of an ancient planetary merger while looking up at another product of the same collision every time the moon rises. It's difficult to find a better example of how a single event can leave evidence in several places at once. Some evidence may be above us, some may be beneath us, and some is locked inside the chemistry of rocks. That chemistry is especially important because Earth has erased much of its earlier surface history. Our planet is geologically active. Crust is created and destroyed, continents change, rock melts, sediments are buried, water and weather alter exposed surfaces. Plate tectonics continually rearranges the outer shell of the planet. Earth is terrible at keeping a tidy scrapbook. The moon is different. It has experienced impacts and volcanism, but it lacks Earth's active plate tectonic system, flowing oceans and thick weather-producing atmosphere. Its surface preserves a much longer visible record. When astronauts brought lunar rocks back to Earth, they gave scientists samples from a world that had retained evidence unavailable on our constantly changing planet. Those rocks helped transform the question of lunar origin from an interesting astronomical puzzle into something that could be tested in laboratories, and the tests produced surprises. One of the biggest is just how similar Earth and Moon material can be in various isotopic systems. Isotopes are versions of the same chemical element with different numbers of neutrons. They behave similarly chemically, but their proportions can provide clues about where material came from and what happened to it. Different regions of the early solar system could develop distinctive isotopic signatures. So, if the Moon were made mostly from a separate object that had formed from noticeably different material, scientists might expect the Moon to preserve a clearer chemical difference from Earth. Yet many measurements show a close Earth-Moon resemblance. That creates a problem for the simplest version of the impact story. If Theia struck Earth and most of the Moon formed from Theia, why does the Moon look so Earth-like in its isotopes? Perhaps the impact mixed everything very efficiently. Perhaps the post-impact material reached conditions that allowed Earth and the Moon-forming disk to become chemically more similar. Perhaps Theia happened to form from material already similar to Earth's. Perhaps the collision was different from the traditional picture. Or perhaps several processes were involved. This is where computer simulations become useful. No one can reproduce the Moon-forming impact at full scale. There isn't a laboratory large enough, and even if there were, the neighbours would probably object. Instead, researchers use physics to simulate collisions between planetary bodies. They change masses, speeds, impact angles, rotation rates, internal structures. They watch how simulated material moves and compare the result with the real Earth-Moon system. Does enough debris enter orbit? Does the debris contain the right mixture of material? Does the resulting system have the right angular momentum? Can it produce something with the Moon's mass? Can it explain the chemistry measured in lunar samples? Every successful constraint narrows the possibilities. Every mismatch forces another look at the assumptions. And slowly, an event that occurred before any human, animal, plant, ocean, or recognizable continent existed becomes slightly less mysterious. Not completely clear, slightly less mysterious. That's an important distinction because Theia is sometimes presented as though scientists know its biography in comfortable detail. You may see an illustration of a neat orange planet labelled Theia approaching a blue proto-Earth from the left, followed by a spectacular collision, and then a tidy moon appearing in the final panel. Very convenient. Very understandable. Also much cleaner than reality. Theia's colour is unknown, its exact size is uncertain, its orbit has to be reconstructed from models, its composition remains debated, the precise impact scenario remains under investigation. Even the timing of lunar formation is something scientists continue refining as new measurements become available. What we have is evidence strong enough to make a giant impact the dominant framework, combined with unanswered questions large enough to keep planetary scientists very busy. That combination is ideal for us. Enough evidence to tell a real scientific story, enough uncertainty that the story is still developing, and conveniently, enough billions of years between us and the collision that there is very little reason to worry about Theia returning for a second attempt. Tonight we'll follow that story from the beginning. We'll look at the solar system before Earth looked like Earth. We'll see how planets grew from a disk of material surrounding the young sun. We'll meet the world scientists called Theia and look at what they can reasonably infer about it. We'll examine what probably happened when it encountered the proto-Earth. We'll follow the debris around the damaged planet and see how that material could assemble into the moon. We'll look at lunar rocks, isotopes, computer simulations, and Earth's deep mantle. And later, we'll consider what the moon did after it formed, because creating a satellite was not the end of Theia's influence. The presence of the moon affected Earth's tides. It exchanged angular momentum with our planet. Earth's rotation slowed over immense spans of time, while the moon gradually moved farther away. The relationship continues today. The collision may be ancient, but the Earth-Moon system is still evolving because of it. That means Theia belongs to a strange category of lost objects. It is gone as an independent world, yet the consequences of its existence are visible every night. If the giant impact picture is broadly correct, then moonlight itself is connected to a collision that occurred when the solar system was young. You don't have to imagine Theia as some ghost planet wandering through space. It isn't hiding beyond Neptune. It hasn't been waiting behind Jupiter for 4.5 billion years. The interesting possibility is almost the opposite. Theia may no longer exist because its material became part of the world beneath you and the moon above you. One planet was lost. 2 connected bodies emerged from the aftermath. But to understand how anything as large as Theia could simply collide with the young Earth, we have to get rid of our modern picture of the solar system for a while. Today, the planets seem wonderfully orderly. Mercury circles close to the Sun, Venus follows, then Earth, then Mars. Farther out are the giant planets. Their paths are predictable enough that astronomers can calculate their positions far into the future. We build spacecraft around that predictability. We know where Mars should be when a probe arrives. We know when planets will line up in the sky. We know when eclipses will occur. It feels like a mature system because that's exactly what it is. But none of that neatness was guaranteed at the beginning. The young sun was surrounded by leftover gas, dust, rock, metal, and growing planetary bodies. Small objects collided to make larger ones. Larger ones collided with each other. Gravity continually altered trajectories. A body that looked like a promising young planet could experience one unfortunate encounter and become raw material for something else. Earth itself grew through collisions. So did the other rocky planets. The boundary between planet and projectile was sometimes mostly a matter of what happened next, and long before there was a moon to brighten Earth's nights, long before the surface cooled into anything we would recognize. The region around the young sun contained more worlds and would-be worlds than the solar system has managed to keep. Some would survive, some would merge, some would disappear. If you could somehow travel back to the solar system as it existed more than 4.5 billion years ago, the first thing you would probably notice is that almost nothing looked finished. There was a sun, although even that was younger and more active than the one we know today. Around it stretched a broad disk of gas, dust, rock, metal, ice, and countless pieces of material moving in roughly the same direction. There were no neat planetary lanes. No familiar collection of 8 worlds. No quiet blue Earth with a moon beside it. There were growing objects everywhere. Some were tiny. Some were large enough to have gravity strong enough to pull themselves into rounded shapes. Others had already become substantial planetary embryos, large bodies that might one day become full planets if they managed to avoid being destroyed, thrown away, or swallowed by something larger. It was a difficult time to be an aspiring planet. The story begins with the formation of the sun itself. Before there was a solar system, there was a large cloud of gas and dust in space. Most of that cloud was hydrogen and helium, with smaller amounts of heavier elements produced by earlier generations of stars. Something caused part of the cloud to collapse under gravity. Exactly what triggered that collapse is difficult to know after more than 4 billion years. It may have been helped by a nearby stellar event, or it may simply have reached a point where gravity took over. As the cloud collapsed, it began rotating faster. You can see a small version of this effect when a spinning ice skater pulls in their arms and speeds up. The physics is called conservation of angular momentum, although the original cloud had considerably more hydrogen and noticeably fewer ice skates. The centre became denser and hotter. Eventually, conditions there became extreme enough for nuclear fusion to begin. The sun switched on, switched. Around it remained a rotating disk of leftover material called the protoplanetary disk. That disk was the construction site from which the planets would eventually emerge. Near the young sun, temperatures were high. Light gases and volatile materials were difficult to retain. The solid material available there consisted mainly of rock and metal. Farther away, where temperatures were lower, water ice and other frozen compounds could survive, providing more material for growing worlds. This basic temperature difference helped produce two very different kinds of planets. Closer to the sun, rocky planets formed. Farther out, much larger planets could grow from rock, ice, and gas. The inner solar system would eventually give us Mercury, Venus, Earth, and Mars. But before those planets reached their modern forms, the region was filled with smaller bodies competing for the same material. The first solid grains were tiny. They collided with one another. Some collisions caused them to stick. Gradually, particles became clumps. Clumps became larger objects. Once some of those objects became large enough, gravity helped the process along. A growing body could pull nearby material toward itself. The larger it became, the more effectively it could gather more. This stage produced objects called planetesimals. Think of them as early building blocks of planets. Some may have been only a few kilometers across. Others became much larger. Over time, repeated collisions and mergers produced planetary embryos, objects that could approach the size of today's Moon or Mars. The process sounds pleasantly gradual when described in a few sentences. Dust becomes pebbles, pebbles become rocks, rocks become planets. Very tidy. The actual process involved a great deal of smashing. Collisions were normal. In fact, collisions were essential. Without them, the planets could not have grown. A planet like Earth is, in one sense, the result of an enormous number of smaller objects repeatedly running into each other and staying together. The difficult part is that not every collision ends with a peaceful merger. At low enough speeds, two bodies might combine. At higher speeds, they might break apart. A glancing impact could strip material from one body. A head-on collision could melt huge regions. A particularly energetic impact could leave behind a completely different object from either of the original participants. Young planets were therefore growing and being damaged at the same time. They gained material. They lost material. They changed their orbits. Their interiors melted and separated into layers. Their surfaces were repeatedly destroyed. Earth went through all of this. The early Earth was not created in a single moment. There was no point at which a perfectly formed planet appeared and simply waited for oceans to arrive. It accumulated. It changed. It became larger through repeated impacts. As that material came together, the planet became extremely hot. Some of the heat came from the energy of collisions. When an object travelling at several kilometers per second hits another large body, its motion is converted into heat, deformation, melting, and sometimes vaporization. More heat came from gravitational compression. Radioactive elements also contributed. The result was an early Earth that may have contained enormous regions of molten rock. This allowed its material to separate according to density. Heavy elements, especially iron and nickel, moved inward. Lighter rocky material remained higher up. That process helped form Earth's metallic core and rocky mantle. The same basic differentiation could happen inside other sufficiently large planetary bodies. Theia, if it had grown large enough before striking Earth, would probably have had its own internal structure as well. It may have possessed an iron-rich core. It may have had a rocky mantle. Its surface may have been molten, partly molten, or repeatedly resurfaced by impacts. We do not know exactly what Theia looked like, but it was probably not simply one enormous lump of undifferentiated stone. By the time of the collision, it may already have been a complex planetary body. This matters because the fate of Theia's core and mantle becomes important later. If its core was mostly metallic, and Earth's core was already forming, then much of Theia's metal may have moved into Earth after the collision. its rocky mantle could have followed a different path. Some of that material may have mixed into Earth's mantle. Some may have been thrown into orbit. The details depend heavily on the impact. But long before that happened, Theia first had to survive the crowded environment around the young sun. The inner solar system contained many large embryos. Earth was not alone. Mars was not alone. Venus was not alone. There were likely several bodies whose names we will never know because they disappeared before humans arrived to give them names. Some were incorporated into the surviving planets. Some may have been thrown into the sun. Some may have collided with each other. Others could have been ejected into distant space. Planet formation is partly a story about the objects that survived, but also about the objects that did not. That can be easy to forget because the modern solar system looks so stable. If you look at a diagram today, Earth appears to have a perfectly sensible position. There it is, third planet from the Sun, Venus inside, Mars outside. Everything seems as though it must always have been arranged that way. But early orbits were less settled. Growing planets pulled on one another gravitationally. Larger planets farther out also influenced the inner system. Every body was responding to every other body, although the strongest effects came from nearby or especially massive neighbours. A close gravitational encounter could alter an orbit. One altered orbit could lead to another close encounter. Eventually, two paths could cross. This is probably how the conditions for the Theia impact developed. Theia did not need to aim for Earth. Planets are generally not known for personal grudges. Its orbit simply had to become unstable enough that the two bodies eventually occupied the same place at the same time. There is one particularly interesting idea about where Theia might have spent part of its early history. Some models have suggested that a body could have formed near one of Earth's gravitationally stable regions around the Sun, sometimes associated with what are called Lagrange points. These are positions where gravitational forces and orbital motion can create relatively stable configurations. The idea is appealing because it offers a way for a substantial object to grow near Earth's orbit before eventually becoming unstable. However, this is not something we know happened. Theia's original orbit cannot be reconstructed with certainty. There are many possible histories capable of producing a collision. What we do know is that large impacts were not unusual during the final stages of rocky planet formation. In fact, they were expected. Computer simulations of planet formation often produce repeated giant collisions among planetary embryos before the surviving planets settle into stable orbits. Earth may have experienced several enormous impacts. The moon-forming event was probably one of the last major ones. That timing is important. If the impact happened too early, Earth could still have experienced many major collisions afterward, potentially disrupting the newly formed moon. If it happened during the later stages of Earth's growth, the system would have had a better chance of surviving into the configuration we recognize today. Scientists have tried to estimate the timing using radioactive dating methods and models of planetary formation. The exact age remains debated, but the event is generally placed very early in solar system history, tens of millions of years after the first solid material formed. That may sound like a long time. On human timescales, tens of millions of years is difficult to imagine. In planet formation, it is early childhood. The entire solar system was still settling down. Jupiter and Saturn already had enormous gravitational influence. Asteroids and planetesimals were being scattered. Rocky planets were still collecting material. The young sun was more active, impacts were frequent. The surface of Earth was changing constantly. There may have been brief periods when parts of the surface cooled enough to begin forming a crust, only for another large collision to heat or melt it again. Any early atmosphere could have been altered repeatedly. Volatile materials could be delivered by impacts or lost because of them. There was no long period of calm yet, and because Earth itself was still growing, it may have looked somewhat different from the planet Theia eventually struck. Scientists often call it the proto-Earth. That simply means an earlier version of Earth that had not yet reached its final mass or structure. The proto-Earth may already have been the larger of the two bodies. In the traditional giant impact model, Theia is often imagined as having roughly the mass of Mars. Mars today is about 1/10 the mass of Earth. That still makes it enormous. Mars has a diameter of nearly 6,800 kilometers. If you placed it beside Earth, it would clearly be the smaller planet, but no one would describe it as a minor object. A Mars-sized body striking Earth would involve an amount of energy far beyond any asteroid impact in human discussion. The asteroid associated with the extinction of the non-avian dinosaurs was perhaps around 10 kilometers across. Theia, in the traditional picture, would have been thousands of kilometers across. The difference is not merely large, it is difficult to express using familiar comparisons. The dinosaur-killing impact changed life on Earth. A collision with a planetary embryo can change the planet itself. And yet, before the impact, Theia may have spent millions of years simply orbiting the Sun. Perhaps it had its own smaller impacts. Perhaps it gathered material. Perhaps it developed a metallic core. Perhaps it had periods when its surface cooled before being reheated. It existed long enough to become a world. Then orbital dynamics brought it closer to Earth. One reason these events become more likely during late-stage planet formation is that as the number of objects decreases, the remaining embryos become larger. Early collisions might involve countless small bodies. Later collisions involve fewer but much more massive ones. It's a bit like clearing a crowded room by repeatedly combining people into larger groups. Eventually, instead of bumping into individuals, you have two entire wedding parties colliding near the buffet. The solar system was doing something much more violent, but the general problem of fewer and larger participants is similar. As embryos grew, their gravitational reach increased. They disturbed neighbouring orbits more strongly. The system became a complicated competition. Some bodies gained stable territories, others did not. Theia appears to have been one of the unsuccessful ones. Earth survived. But saying Earth survived does not mean Earth escaped unchanged. A giant impact can be both destructive and constructive. The collision would destroy much of the recognizable structure of the impactor. It would seriously disturb Earth. At the same time, it could contribute additional material to Earth and provide the debris that became the Moon. This is one of the unusual features of planetary formation. Destruction and creation are often the same event viewed at different scales. A collision destroys two earlier configurations. Gravity then reorganizes what remains. From the viewpoint of Theia, it is disaster. From the viewpoint of the future Earth-Moon system, it is a beginning. There is another reason the young solar system was so different from the one we see today. There was far more leftover material. Most of it is gone now. Planets absorbed it. The Sun absorbed some of it. Some objects were ejected. Others remain in smaller reservoirs such as the asteroid belt and distant populations beyond Neptune. But early on, much more debris moved between the growing worlds. Every surviving planet carries evidence of that violent period. Look at Mercury. Its enormous metallic core compared with its thin rocky mantle has led scientists to consider whether major impacts help strip away part of its outer material, although other explanations are also studied. Look at Mars. Its northern and southern hemispheres are dramatically different in elevation and crustal thickness, and giant impacts have been proposed as one possible contributor. Look at Uranus, much farther from the Sun. It rotates on its side, and one long-standing explanation involves one or more enormous collisions during its formation. Planetary systems are full of worlds that appear to have experienced dramatic events. Earth is not the calm exception. Our planet simply repaired the evidence more efficiently. Plate tectonics recycles crust. Erosion destroys old surfaces. Volcanoes cover older rock. Oceans reshape landscapes. Life itself alters the chemistry of the atmosphere and surface. Earth has been continuously editing its own history. The Moon, with its ancient cratered surface, provides a clearer reminder of what the early solar system was like. Mercury does too. So do many moons and asteroids. Their battered surfaces tell us that collision was once an ordinary part of planetary life. Earth's surface would once have been battered as well. We just don't have most of those early craters anymore. They're gone. The rocks were melted, buried, folded, eroded, or recycled. So when scientists reconstruct the environment in which Theia existed, they rely on several kinds of evidence. They study meteorites, some of which preserve extremely ancient material from the beginning of the solar system. They date lunar samples. They examine isotopic ratios. They model the dynamics of growing planets. They observe young planetary systems around other stars. Those distant systems are especially helpful because astronomy has given us a way to see different stages of planetary development. We cannot watch our own solar system form again. That event happened once. But we can observe young stars surrounded by disks. We can see gaps and structures in those disks that may be associated with growing planets. We can study systems where planets appear to be migrating or interacting. The details differ from system to system, but the broader lesson is clear. Planet formation is active. It is not simply a quiet process in which each planet grows exactly where we find it today. Even our giant planets may have shifted their orbits significantly during the solar system's early evolution. If Jupiter and Saturn moved, their gravitational influence could have scattered huge numbers of smaller bodies. Models such as the Grantak hypothesis and later instability models attempt to explain parts of this early rearrangement. Scientists debate the details. The exact movements of the giant planets are not known with certainty, but there is strong reason to think the early solar system experienced significant dynamical evolution. That makes Theia easier to understand, not because we know its exact path, but because a wandering or destabilized planetary embryo is not an absurd exception. It is precisely the kind of thing early planet formation can produce. The young solar system contained worlds that were still negotiating where they were allowed to exist. The negotiations were conducted entirely through gravity. Gravity is extremely patient. Two bodies can orbit safely for a very long time, while small gravitational effects accumulate. A tiny change in speed can become a large change in position after enough orbits. Repeated encounters can gradually increase an orbit's eccentricity, making it less circular. Eventually, an orbit that once seemed safe can cross another. Once that happens, a collision is not guaranteed immediately. The bodies still have to arrive at the crossing point at the same time. They might miss one another again and again, but every orbit offers another opportunity. Given enough time, the odds become uncomfortable. Theia and the proto-Earth may have passed near one another before the final collision. We cannot know. Perhaps their gravity altered each other's paths gradually. Perhaps Theia was perturbed by another embryo. Perhaps the giant planets indirectly contributed. There are many routes to the same ending. Eventually, however, the geometry became unforgiving. The two worlds approached. Their mutual gravity accelerated them toward one another. As the distance shrank, the attraction became stronger. Theia could not simply tap the brakes. There were no engines, no steering system, no helpful planetary traffic controller suggesting a slight adjustment to the left. Only momentum and gravity. By then, Earth may already have had an atmosphere of some kind, though nothing we would want to breathe. Its surface conditions were extremely hot. Its interior was actively differentiating. Theia may have been in a similar state. Both bodies were products of the same chaotic environment. Both had survived countless smaller collisions. Both had accumulated material over millions of years. For most of their existence, neither had any special role. They were simply two growing worlds among several. Our tendency to think of Theia as destined to create the moon comes from knowing the ending. But nothing about the early solar system was working toward that result. There was no plan requiring Earth to have a large satellite. Had Theia missed Earth, our planet might have evolved very differently. Theia itself might have survived longer. It might have collided with Venus. It might have struck another embryo. It might have been scattered out of the inner solar system. Perhaps it could even have remained as a separate planet, leaving the modern solar system with an arrangement completely unfamiliar to us. But that is not the system we inherited. Theia's path crossed Earth's, and as the two bodies moved closer, the scale of the coming event became enormous. At planetary distances, things still appear slow. You could imagine Theia hanging against the blackness of space, growing gradually larger as it approached. But the actual relative velocity would have been measured in kilometers per second. There would be no dramatic pause before contact, no moment when the planets hovered near one another. Once they were close enough, the collision would unfold rapidly. The outermost material would make contact first. Pressure waves would move through rock. The surfaces would deform. Rock that normally seems solid would behave like an intensely compressed fluid. Temperatures would rise. Material would be accelerated outward. If the impact angle was oblique, as many models suggest, Theia could strike the side of the proto-Earth rather than hitting directly through its center. That distinction changes everything about the debris. But before we get into the impact itself, there is one more thing worth keeping in mind. Theia was not merely an object that happened to hit Earth, it was another product of the same process that built Earth. It formed from the same broad disk around the young sun. It grew through collisions. It was shaped by gravity. It may have separated into layers. It spent millions of years developing as a planetary body. And then, after all that formation, its independent history ended in a matter of hours. The young solar system was full of stories like that. Most have been erased. Theia's is unusual because one enormous clue survived. It is still orbiting us. The moon does not tell us everything about the lost planet, but its existence gives us a place to begin asking what Theia was actually like, how large it may have become, what it may have been made of, and why this particular lost world ended up on a collision course with the proto-Earth. The moon gives us a reason to believe Theia existed, but reconstructing Theia itself is much harder. There are no Theian rocks sitting in a museum with little cards underneath them. No spacecraft ever photographed its surface. No crater map survives. We cannot say whether it had enormous volcanoes, broad lava plains, towering mountains, or a particularly impressive collection of early solar system potholes. Even the name Theia is something humans gave it billions of years after it disappeared. So when scientists describe this lost world, they have to work backward from the things that survived the collision. The modern Earth, the moon, their chemical compositions, their internal structures, their motion around each other, and the laws of physics that determine what happens when two planetary bodies collide at several kilometers per second. From those clues, a rough picture emerges. Theia was probably a planetary embryo, meaning an object that had grown beyond the stage of an ordinary asteroid, but had not necessarily reached the final state of a mature planet. In the traditional version of the giant impact model, it was roughly comparable in mass to Mars. That's worth putting into perspective. Mars is the second smallest planet in the modern solar system, but calling something Mars-sized can make it sound more modest than it really is. Mars is nearly 6,800 kilometers across. It contains mountains, valleys, polar ice caps, volcanoes, enormous impact basins, and enough surface area to make getting lost there a serious inconvenience. If Theia really approached that scale, Earth was not struck by an unusually ambitious asteroid. It was struck by another world. There are alternative impact models in which the bodies had different relative masses, so we shouldn't imagine that scientists possess Theia's exact birth certificate, with weight and measurements neatly recorded. They don't. A Mars-sized impactor is a useful and historically important version of the idea, but researchers test a range of possibilities. The collision has to reproduce several things at once: the mass of the moon, the chemistry of the moon, the angular momentum of the Earth-Moon system, Earth's rotation, the distribution of material between the surviving Earth and the orbiting debris. Change the size of Theia, and you change almost everything else. A larger impactor carries more momentum. It contains more metal and rock. It produces a different amount of debris. It transfers a different amount of energy. A smaller one behaves differently again. Scientists therefore treat Theia's size as something constrained by models rather than a number carved into ancient stone. Its composition is even more interesting. Because Theia formed somewhere in the inner solar system, it was probably made mainly of silicate rock and metal, broadly like the rocky planets we see today. As it grew, heating from impacts, radioactive elements, and gravitational energy may have allowed much of its interior to melt. If that happened, dense metallic material would sink toward its centre, while lighter silicate rock remained above. The result would be differentiation, a core, a mantle, possibly some kind of early crust. In other words, Theia may already have developed the basic internal arrangement we associate with a planet. Theia's metallic core becomes particularly important because the Moon has a relatively small metallic core compared with Earth. Whatever created the Moon had to produce a satellite made mostly of rocky material, rather than simply tossing an equal mixture of iron and silicate into orbit. A glancing giant impact provides one possible way to do that. The outer rocky portions of two bodies can be disturbed and thrown outward, while much of the denser metallic material remains with, or eventually sinks into, the larger surviving planet. That doesn't mean every atom politely followed instructions. Giant impacts are not known for their administrative efficiency. Material would have been mixed, heated, melted, vaporized, scattered, and redistributed. But the general difference between dense core material and rocky mantle material helps scientists understand why the Moon ended up as a mostly silicate body, with a much smaller iron-rich core than Earth. The next question is where Theia came from. This is where things become less certain. We know Earth formed in the inner solar system from material orbiting relatively close to the young Sun. Theia probably formed in the same broad region, but the same broad region can still cover an enormous amount of space. A small difference in formation distance can matter, because the early solar system was not chemically identical everywhere. Different materials condensed at different temperatures. Different populations of planetesimals developed different isotopic signatures. A body forming somewhat closer to the Sun might therefore have a slightly different chemical fingerprint from one forming farther away. Those fingerprints are one of the few ways scientists can investigate Theia's origin after the planet itself has disappeared. And this leads to a problem that has followed the giant impact hypothesis for decades. Earth and Moon rocks are remarkably similar in several isotopic systems. If the Moon formed largely from Theia, and if Theia formed somewhere chemically distinct from Earth, you might expect the Moon to carry a noticeably different isotopic signature. Yet in many measurements, that difference is very small. Sometimes it is difficult to detect at all. This forced researchers to consider several possibilities. Perhaps Theia formed extremely close to Earth, and therefore started with almost the same composition. Perhaps the impact was energetic enough to mix material from the two bodies more thoroughly than early models assumed. Perhaps the Moon contains more proto-Earth material than the simplest impact scenarios predicted. Or perhaps small isotopic differences between Earth and the Moon do survive, and increasingly precise measurements are beginning to uncover them. There is evidence supporting more than one piece of that picture. Some research has found small differences in oxygen isotopes between lunar and terrestrial material, and has proposed that deeper lunar material may preserve more of Theia's original isotopic signature. If that interpretation is correct, Theia may not have been chemically identical to Earth after all. It could have formed at a somewhat different distance from the Sun before orbital evolution eventually brought the two worlds together. Other isotopic studies point toward Theia and Earth having formed from broadly similar material in the inner solar system. Vanadium measurements, for example, have been interpreted as being compatible with a canonical giant impact in which a substantial fraction of lunar material came from the impactor, while Earth and Theia themselves originated from a shared inner solar system reservoir. That may sound like scientists are giving several different answers. In a way they are. But that is not a weakness of the investigation. It's what happens when you're trying to reconstruct an event more than 4 billion years old using tiny chemical differences preserved in rocks. Every isotope system behaves differently. Oxygen does not respond to planetary processes exactly like tungsten. Tungsten does not behave exactly like titanium. Vanadium brings another set of clues. Each element has its own chemical preferences. Some move readily into metallic cores. Others remain mainly in rocky mantles. Some can be altered by evaporation. Some preserve information about when core formation happened. You can think of them as witnesses who are standing in different parts of the room. None saw everything. But together, they can tell us much more than one witness alone. Tungsten is particularly useful because one of its isotopes is connected to the radioactive decay of hafnium-182, which existed during the early history of the solar system. Because tungsten tends to enter metal during core formation, while hafnium tends to remain in silicate rock, tungsten isotopes can preserve information about when a body's core separated and how that body grew. Researchers have used this relationship in computer models of Earth and Theia's accretion. Those studies demonstrate just how difficult it can be for a conventional impact to produce a moon with isotopic properties so close to Earth's if Theia had evolved very differently. That difficulty is one reason the exact moon-forming scenario remains under investigation. Theia therefore sits in an unusual scientific position. We are fairly confident that something enormous struck the young Earth. We can give that impactor a name, we can estimate plausible masses, we can model its interior, we can study what its chemistry might have been, but almost every detail becomes a range of possibilities rather than a single answer. Even its appearance is unknowable. Popular illustrations often show Theia as a glowing orange or red planet. That makes sense artistically. Red means hot, orange means dangerous. And apparently nobody has ever looked at a planetary collision illustration and thought, you know what would really improve this? Beige. But Theia's true visible surface is impossible to reconstruct. If it was still very hot, it may have had widespread molten regions. If enough time had passed for parts of the surface to cool, solid crust may have existed. Large impacts could have repeatedly broken and melted that crust. It might have had a temporary atmosphere produced by outgassing from molten rock. Any such atmosphere would have been nothing like modern Earth's oxygen-rich air. Carbon dioxide, water vapour, carbon monoxide, hydrogen, sulfur-bearing gases and other materials could have been present depending on its composition and temperature. But again, these details are possibilities based on our understanding of young rocky worlds. We do not have a direct sample from Theia's atmosphere. The poor thing disappeared several billion years before anyone invented weather balloons. What we can say with more confidence is that gravity would have pulled Theia into something close to a sphere once it became sufficiently massive. It would have orbited the Sun. It would have possessed its own gravitational field. And if it had differentiated, it would have behaved internally much more like a small planet than a loose pile of asteroid rubble. Its surface gravity, however, would have been weaker than Earth's. If Theia were roughly Mars-sized, standing on it would have felt somewhat similar to standing on Mars. You would weigh much less than you do on Earth. This would be exciting for approximately 3 seconds before you remembered that there was probably no breathable atmosphere. The surface might be partly molten, and another planet was eventually going to arrive at considerable speed. Theia's orbit is another puzzle. To hit Earth, it needed an orbit that eventually intersected Earth's. That doesn't necessarily mean it spent its entire existence crossing Earth's path. An orbit can evolve. The gravitational influence of other planetary embryos can slowly alter it. The growing planets perturb one another. Resonances can amplify changes. A close encounter can suddenly shift a body's path. During the chaotic final stages of terrestrial planet formation, these changes were common enough that giant impacts are a natural outcome in many simulations. Imagine several large bodies moving around the Sun on neighbouring tracks. They are not sitting still relative to each other. Each one is continuously pulling gravitationally on the others. Most of those pulls are small, but small effects repeated over thousands or millions of orbits can matter. Perhaps Theia originally followed a fairly stable path. Then another embryo passed nearby. Its orbit changed slightly. That new orbit brought it closer to Earth. Earth's gravity altered it again. A later encounter changed things further. Eventually, what had once been 2 neighbouring worlds became 2 objects with intersecting trajectories. There does not need to be a single dramatic event that sent Theia directly at Earth. Orbital instability can build gradually. This is one reason the phrase "Theia hit Earth" can give the wrong impression. It makes Theia sound like a projectile fired from somewhere else. In reality, both bodies were orbiting the Sun. Earth was moving too. The collision occurred because two planetary trajectories intersected at exactly the wrong time. From the Sun's perspective, both worlds were moving around it at tens of kilometers per second. Their speed relative to one another during the final encounter would depend on the exact orbital geometry. As Theia approached Earth, Earth's gravity would accelerate it further. By the moment of impact, the relative speed was probably comparable to Earth's escape velocity, or somewhat higher in many models. That means around 10 kilometers per second is a useful order of magnitude to keep in mind. At that speed, crossing the entire width of a modern city takes seconds. Crossing an ocean takes minutes. There would be no long cinematic sequence in which two planets slowly drift toward each other while someone has time to give an emotional speech. The interesting part is that Theia may have spent millions of years existing as a separate world before those final hours. Planetary embryos do not form instantly. Theia had to gather material. It had to survive other impacts. It had to avoid being swallowed by another body earlier. It may have developed its core. It may have cooled and reheated several times. It had a history. We just don't know most of it. That missing history makes Theia very different from the planets that survived. Mars, Venus, Mercury and Earth can still be studied as individual worlds. We send spacecraft to them. We map their surfaces. We measure their atmospheres. We infer their interiors. Theia can only be reconstructed from consequences, and perhaps from material that is no longer obviously Theian. Suppose a large fraction of Theia's rocky mantle entered Earth. After more than 4 billion years of mantle convection, melting, chemical differentiation, volcanism, and plate tectonics, identifying those atoms would be extremely difficult. They would not remain in a neat underground layer labelled Theia. Much of the material could mix into Earth's mantle, but complete mixing is not always guaranteed. Earth's mantle is solid rock over most of its depth, even though it moves slowly over geological time. Different regions can preserve chemical differences for extraordinary periods. This is where an especially interesting possibility enters the story. Deep inside Earth, near the boundary between the mantle and the core, seismic measurements reveal two enormous regions where seismic waves travel unusually slowly. They are called large low-velocity provinces, usually shortened to LLVPs, because geophysicists apparently decided that something thousands of kilometers beneath us should have a name that requires a small warm-up exercise for the tongue. One lies broadly beneath Africa, the other lies beneath the Pacific. They are enormous. Each is comparable in horizontal scale to a continent. Scientists know these structures are there because earthquake waves behave differently when passing through them. What scientists do not yet know with certainty is exactly what they are made of or how they formed. Several explanations exist. One hypothesis published in 2023 proposed a remarkable possibility. The LLVPs may contain ancient material from Theia. Computer simulations in that study suggested that if Theia's mantle was denser than the Proto-Earth's mantle, some large pieces could have survived the impact without becoming completely mixed. Those dense pieces could then have sunk toward Earth's core and accumulated in the lower mantle. Mantle convection models suggested that such material could potentially survive for billions of years. This does not mean scientists have drilled into an LLVP, pulled up a rock, and announced that Theia has been found. The deepest hole humans have drilled doesn't come remotely close to the lower mantle. The interpretation remains a hypothesis. There are other explanations for the LLVPs. They could involve material generated by Earth's own internal evolution. They could contain mixtures of several sources. Their exact structure and composition remain subjects of active research. Still, the idea creates an extraordinary possibility. Theia may be above us and below us at the same time. Part of its silicate material may have contributed to the Moon. Another part may have entered Earth. Its metallic core may have joined Earth's core. If remnants of its mantle survived in the deep interior, then Theia didn't simply vanish. It was dismantled. Its identity as a separate planet disappeared, but its material was redistributed. This distinction is useful because planets are not individual objects in quite the same way living organisms are. A planet has no fixed set of atoms that must remain together forever. Earth itself constantly gains and loses tiny amounts of material. Meteorites fall onto it. Atmospheric particles escape. Rock melts. Continents move. Material circulates through the mantle. The atoms persist while the structures change. Theia's structure was destroyed. Its atoms did not disappear. Some were probably thrown away from the system. Some may have remained in orbit. Some entered Earth. The Moon became the most obvious surviving result. That makes the word lost slightly misleading. The planet is lost as a planet. Its matter may be all around us. This also explains why scientists are so interested in obtaining new lunar samples from different regions and greater depths. The Apollo missions were revolutionary, but astronauts collected samples from a limited number of locations, all on the Moon's near side. Every new sample gives researchers another opportunity to compare lunar material with Earth. If scientists can find parts of the lunar mantle that have been less altered by later melting and volcanic activity, those rocks might preserve clearer evidence of the Moon's original ingredients, and somewhere in those ingredients may be Theia. The idea is a bit like trying to reconstruct two cakes after someone mixed them together, baked the mixture, dropped half of it on the floor, put the other half in a blender, and then left the kitchen untouched for 4.5 billion years. Except isotopes are much better evidence than crumbs. The comparison is also unfair to planetary scientists, who tend to run cleaner laboratories. What they are trying to determine is how much of the Moon came from the proto-Earth and how much came from Theia. Early canonical simulations often produced a moon-forming disk, containing a large proportion of material from the impactor. That makes intuitive sense. The smaller body strikes Earth. Its outer rocky layers are disrupted. Much of that material enters orbit. A moon forms largely from the impactor, but the strong chemical similarity between Earth and Moon then becomes awkward. If the Moon is mostly Theia, why does it resemble Earth so much? This question drove the development of alternative impact scenarios. Some models make the proto-Earth rotate extremely quickly before the collision. Others involve higher energy impacts. Some produce a structure called a synestia, a huge rotating mass of vaporized and molten silicate created when an impact pushes a planetary body beyond the point where it can maintain an ordinary compact shape. In those models, the Moon can form within an extended cloud of thoroughly mixed terrestrial and impactor material. Other models stay closer to the traditional Mars-sized impactor and look for ways to explain the isotopic similarity through the original compositions of Earth and Theia. None of this changes the basic role Theia plays in the story. It reminds us that Theia is not one precisely reconstructed planet. It is the name given to the moon-forming impactor, while scientists work out what that impactor must have been. Its properties are part of the mystery, and that makes Theia much more interesting than a simple doomed Mars-sized world travelling obediently toward Earth. It may have been smaller. It may have been larger. It may have formed close to Earth. It may have formed farther away. It may have been chemically very similar to Earth. It may have preserved measurable differences. Parts of it may remain in the Moon. Parts may remain deep inside Earth. The details are still being tested because each new measurement changes the limits of what the collision could have looked like. There is something else we can infer about Theia from the fact that the Moon exists at all. Its final encounter with Earth probably was not perfectly head-on. A direct central collision between two massive bodies tends to send much of the material inward and can make it difficult to place the required amount of rocky debris into a stable orbit. A more oblique collision transfers angular momentum more effectively. Theia can strike Earth's outer regions, deform both bodies, and send substantial silicate material outward. The exact angle depends on the model, but the collision is often depicted as a glancing blow for this reason. That means the final moments would have looked nothing like one planet simply disappearing into another. Theia would begin interacting with Earth's outer layers. Its mantle would stretch, and deform. Earth's mantle would do the same. Shock waves would travel through both worlds. Temperatures would rise high enough to melt and vaporize vast amounts of rock. Some material would move outward faster than Earth's local escape speed and disappear into independent orbits around the Sun. Some would remain gravitationally bound to Earth. Some would rain back onto the planet. Theia's core would continue moving through an environment that no longer behaved like the solid worlds it had been moments earlier. At those pressures and temperatures, the familiar idea of rock as something hard and stationary becomes useless. Planetary mantles can flow, they can be torn apart, they can form long streams of material, they can briefly produce atmospheres made from rock vapor. The collision would turn two organized planetary interiors into a complicated, rapidly changing mixture. And somewhere during that process, Theia would stop being Theia. There would probably be no single instant when you could point at the event and say, "There, that was the exact second the planet ceased to exist." At first it was a separate body, then it was deeply deformed, then disrupted, then its material was spread through Earth and surrounding space. Its core merged or sank, its mantle fragmented, its independent gravitational identity disappeared. Afterward, only pieces of its former structure remained. For billions of years, that would be the end of the story as far as anyone knew. Then one species appeared on Earth, looked at the moon, collected some rocks, developed isotope mass spectrometers and giant impact simulations, and gradually realized that the quiet object in the night sky might be evidence of a missing planet. We gave that planet a name, Theia, not because we'd found it, because we'd found what happened to it. By the time Theia and the Proto-Earth entered their final encounter, there was no longer any realistic way for either world to avoid what was coming. Both were moving around the Sun. Both carried enormous momentum. Their own gravity was pulling them toward one another, increasing their relative speed as the distance between them fell. In the widely used traditional giant impact model, Theia was approximately Mars-sized, and struck the young Earth in an off-center collision near the mutual escape velocity of the two bodies. The exact geometry remains under investigation, but this general type of collision can place enough rocky material around Earth to begin explaining the origin of the Moon. It helps to forget almost everything our daily experience teaches us about collisions. When two cars collide, metal bends. When two stones collide, they may crack. When two planets collide, the pressures and energies are so large that even solid rock stops behaving in a comfortably familiar way. The outer surfaces meet first, but there is no ordinary surface left for long. Theia presses into the Proto-Earth at several kilometers per second. Material is compressed almost instantly. Powerful shock waves move through both bodies. Rock heats, melts, deforms, and under sufficiently energetic conditions, some of it becomes vapor. This is not simply a large version of a meteorite making a crater. A crater assumes that after the impact you still have a reasonably recognizable target with a hole in it. Here, the impactor itself is a substantial fraction of a planet. The target is violently reshaped. The projectile is torn apart. For a short period, the distinction between Theia and Earth becomes increasingly difficult to maintain. Imagine trying to throw a snowball into another snowball so hard that both partially melt, spread outward, mix together, and reorganize themselves under gravity. Then replace the snow with planetary mantles, increase the temperature by several thousand degrees in places, make one snowball roughly the size of Earth, and remove the part where you stand nearby to watch. You would not want nearby seats for this particular demonstration. The collision probably did not begin with the centers of the two worlds perfectly aligned. That off-center geometry is important. If Theia had struck directly through Earth's center in a simple, head-on collision, much more of its momentum would have been directed inward. An oblique impact is better able to transfer angular momentum and throw substantial material from the rocky outer regions into orbit. Classic simulations therefore explored a glancing impact in which a roughly Mars-mass body hit a nearly formed Earth at about a 45-degree angle and around the mutual escape speed. Modern research continues to test other masses, angles, speeds, initial spins, and impact conditions. From far away, an off-center collision might initially look almost like Theia was trying to brush past Earth. It would fail rather spectacularly. The near side of Theia would enter Earth's outer layers first. The contact region would experience crushing pressures. Material in front of the impactor could not simply move aside fast enough, so it would be compressed and heated. Theia itself would begin stretching and deforming. Earth would deform too. At these scales, gravity makes planets round over long periods, but during an impact, enormous forces can temporarily turn them into shapes that would look completely wrong to anyone accustomed to seeing neat spheres in astronomy books. Theia's rocky mantle could be smeared into long streams. Earth's outer mantle could be lifted and accelerated outward. Some material would rise far above the damaged planet. Other material would plunge inward. The two metallic cores would have their own interaction deeper in the event. If Theia had already differentiated into an iron-rich core surrounded by a silicate mantle, as giant impact models commonly assume, much of its dense metal would tend to remain with the larger surviving body rather than becoming part of the orbiting moon-forming material. Simulations model both Proto-Earth and Theia as differentiated objects precisely because the distribution of metal and rock affects the resulting Earth and debris disk. Theia's core would not bounce off Earth's core like a steel marble. It would enter an environment of extreme pressure and temperature where metal itself can deform and flow. Depending on the impact geometry, the impactor's core could be disrupted, stretched, and deposited into the deeper regions of the surviving Earth. Over time, dense metallic material would tend to move downward. Earth's existing core would gain material. Theia's identity would be erased even there. Its metal would no longer belong to a separate planet. Its mantle would no longer surround its own center. The organization that had made Theia a world was being dismantled. That is really what it means for a planet to be destroyed. The atoms do not vanish. The rock does not cease to exist. The planet stops being one gravitationally organized object. Its material goes elsewhere. Some of Theia went into Earth. Some entered the enormous cloud and disk of material around Earth. Some material from Earth joined it. And some debris may have escaped the immediate Earth system entirely. NASA's overview of lunar formation describes the impact as throwing molten and vaporized material into space, while impact simulations divide the aftermath among material reaccreted by Earth, material remaining in orbit, and material that escapes. The amount of energy involved is difficult to communicate without simply producing very large numbers and hoping everyone nods thoughtfully. A planet moving at around 10 kilometers per second covers 10,000 meters every second. At that speed, London to Paris would take well under a minute if geography, atmosphere, international borders, and the requirement to remain alive were temporarily ignored. Now give the moving object planetary mass. Its kinetic energy becomes enormous, and when that motion is interrupted, the energy has to go somewhere. It goes into heating, melting, vaporization, deformation, shock waves, motion of debris, changes in rotation, changes in internal structure. The collision transforms orbital energy into an entirely new planetary arrangement. Evidence that the Moon experienced extensive melting is preserved in lunar rocks. Apollo samples and later observations support the conclusion that the early Moon possessed a deep magma ocean, exactly the sort of thermal state expected after an extremely energetic formation event. Lunar material is also depleted in several easily vaporized elements, another clue that high temperatures played an important role in its history. But the temperature was not uniform. Nothing about the aftermath was uniform. Some regions would be hotter than others. Some material would remain liquid. Some would be vaporized. Some could remain in large coherent fragments. Different simulations produce different proportions because the outcome is sensitive to the starting conditions. A slight change in Theia's spin can alter what happens. A change in the impact angle can change the amount of orbiting material. A different impact velocity can change how much rock is melted or vaporized. Even the thermal state of Earth and Theia before contact matters. This is why computer simulations are so important. Scientists cannot simply say, a Mars-sized object hit Earth, and consider the problem finished. They have to ask whether that particular collision produces the Earth-Moon system we actually observe. A successful model has to do several jobs at once. It needs to leave approximately 1 Earth mass in the main surviving body. It needs to create enough orbiting material to account for the Moon. The orbiting material cannot contain too much iron. The resulting system needs an appropriate amount of angular momentum. The eventual Moon must end up with chemistry compatible with lunar samples. Earth must have a plausible rotation state. And after billions of years of tidal evolution, the system has to be capable of resembling the Earth and Moon we have today. NASA specifically notes that moon formation models must reproduce both composition and the orbital and rotational properties of the present Earth-Moon system. Planets, it turns out, are demanding customers. Even after you've crashed 2 of them together, they still expect the paperwork to balance. One particularly important quantity is angular momentum. You can think of angular momentum as a measure connected to rotation and orbital motion. Earth spins. The Moon orbits Earth. Together those motions contain angular momentum. Although the distribution has changed substantially over billions of years because of tides, the total angular momentum of the Earth-Moon system provides a major constraint on models of the original collision. Too little, and the resulting system does not work. Too much, and you need a convincing mechanism for removing the excess later. This is one reason the collision angle matters so much. A glancing blow can give Earth a strong rotational kick while sending material around it rather than simply driving everything inward. Picture pushing a door. Push directly beside the hinges and not much happens. Push near the outer edge and the door rotates easily. The analogy is imperfect because doors rarely contain molten silicate mantles, but the importance of where force is applied is similar. Theia striking away from Earth's centre could transfer substantial rotational motion to the combined system. The young Earth after the impact would probably have rotated much faster than Earth does now. Our familiar 24-hour day came much later. Tidal interaction with the Moon has gradually slowed Earth's rotation, while transferring angular momentum to the Moon's orbit, causing the Moon to move farther from Earth. Measurements using lunar laser ranging confirm that this outward movement is still happening today. So when Theia struck, it did more than add material. It changed how Earth spun. That is a remarkable thing to consider. The length of the day you experience now is connected through billions of years of tidal evolution to a planetary collision that happened before Earth had anything resembling its modern surface. Theia did not create the 24-hour clock, obviously. Humans can take responsibility for that particular scheduling decision. But the ancient impact helped establish the rotating Earth-Moon system from which our modern day length eventually evolved. During the collision itself, however, there were no days in the familiar sense. No one could stand on the surface and watch a sunrise. Much of the exterior was being melted or destroyed. Any atmosphere present before the collision would have been severely disturbed. Hot material surrounded the planet. Earth would have radiated enormous amounts of thermal energy into space. And above the surface, something new was beginning to appear. Not a moon yet. Debris. A tremendous amount of it. One useful distinction is between material that was launched into space and material that was actually placed into orbit. Those are not the same thing. Throw a ball upward and it enters the air, but unless you throw it sideways fast enough, gravity brings it back down. Orbit is essentially continuous falling combined with enough sideways motion to keep missing the planet. The same principle applies to impact debris. Some material blasted away from Earth would travel outward only temporarily. It would rise, slow, reverse direction, and fall back. Other material would be moving so quickly that it escaped Earth's gravity altogether. The crucial fraction occupied the middle ground. It was thrown outward with enough sideways velocity to remain gravitationally bound without immediately crashing back into the planet. That material could orbit. And because the collision was off-center, A substantial amount of angular momentum could be carried by this debris. Now Earth had something it had not possessed before, a large amount of extremely hot rocky material circling it. NASA describes the moon-forming event as launching molten and vaporized debris into space around the young Earth, with that debris later producing the moon. Some newer high-resolution simulations also explore outcomes in which large, orbiting clumps can form very rapidly after the impact rather than requiring every part of the moon to assemble gradually from a smooth disk. This is an important point because the familiar picture of lunar formation has changed, as simulations have improved. The older, simple version often goes like this. Theia hits Earth. A disk of debris forms. The debris slowly gathers. The moon appears. That is still a useful basic description, but modern models show that the actual behaviour could be much more complicated. The debris does not have to be a perfectly smooth ring. Large clumps can emerge. Material can collide again. Some of it can be thrown outward, some can fall back. Some simulations produce temporary moons or large self-gravitating structures. In a high-resolution simulation highlighted by NASA and Durham University, material from Earth and the impactor was launched directly into orbit, allowing a moon-like satellite to form on a timescale of hours in that particular model. That does not establish that our moon definitely formed that quickly, but it shows how sensitive the answer is to the physics and resolution of the simulations. Even the collision itself can unfold differently depending on Theia's rotation before impact. A 2020 set of simulations examined the effect of giving Theia different initial spins while keeping other major conditions similar. Some cases merged efficiently, others left significant material outside the main Earth. One sufficiently rapidly rotating configuration produced more of a hit-and-run outcome. Only a few hours after first contact, the simulated planets could already look dramatically different from their starting forms. That gives us a useful sense of the timescale. Theia may have existed independently for millions of years. Then within hours of contact, its planetary structure could be largely gone. There is something slightly unfair about that. Millions of years spent collecting material, separating a core and mantle, surviving the chaotic inner solar system, perhaps becoming a perfectly respectable small world. Then one extremely bad afternoon. Although afternoon requires a stable surface, a functioning clock, and a reasonably relaxed attitude toward the local magma conditions. So perhaps we shouldn't push the comparison too far. The loss of Theia did not mean Earth simply returned to normal once the impact was finished. There was no normal to return to. The collision produced a new Earth. Its mass had changed, its rotation had changed, its internal material had been mixed and heated, its surface had been extensively melted, its surroundings were filled with debris. Theia's metal and rock were now becoming part of the Earth system. This is why calling the event a collision between Earth and Theia can be slightly misleading if we imagine modern Earth surviving intact. The object that was struck was the proto-Earth. The object that emerged was an important step toward the Earth we know. The planet beneath us is in part the result of what happened that day. Scientists have even proposed that some large portions of Theia's mantle may have survived the violence without completely mixing into Earth's mantle and eventually sunk deep into the planet. That hypothesis concerns the enormous low shear velocity regions near Earth's core mantle boundary that we discussed earlier. Whether those structures truly contain ancient Theian material remains uncertain, but the proposal reminds us that giant impacts do not necessarily blend everything into one perfectly uniform planetary soup. Large pieces and chemically distinct reservoirs can sometimes survive or reform after violent mixing. And that matters when we try to explain both Earth's internal structure and the composition of the Moon. The Moon itself presents one of the collision's most stubborn puzzles. Many traditional giant impact calculations produced orbiting debris with a large contribution from Theia. Yet lunar samples are extremely similar to Earth's mantle in several isotopic measurements. If Theia had a noticeably different composition, why is the Moon not more noticeably Theian? This has led to decades of work on different possibilities. Perhaps Theia happened to resemble Earth chemically. Perhaps Earth and Theia mixed more thoroughly during the impact. Perhaps high temperatures allowed material in the post-impact system to exchange and equilibrate. Perhaps the Moon contains more proto-Earth material than traditional low-resolution simulations suggested. Or perhaps the small differences are there, but they require very precise measurements to reveal. The collision has to explain all of this without losing sight of the basic physical problem. The Moon exists. It is large compared with Earth. It contains relatively little iron compared with our planet. It formed very early. Its rocks show evidence of extensive melting. Its composition closely resembles Earth's mantle, and it carries, together with Earth's rotation, the angular momentum that the ancient impact somehow had to produce or redistribute. That is why the giant impact hypothesis is not simply a dramatic story scientists enjoy because it makes good animations. It became the leading framework because a massive collision can naturally connect several otherwise puzzling properties of the Earth-Moon system. But the exact version of that collision remains open. In science, a broad explanation can be well supported while important details remain unsettled. We know evolution occurs without knowing every detail of every ancestral population. We understand stars through nuclear fusion without knowing the complete life history of every star. And we can have strong evidence that a giant impact created the Earth-Moon system without possessing a frame-by-frame recording of Theia's final approach. The job is to keep narrowing the possibilities. Better lunar samples help. Better measurements help. Better simulations help. Improved knowledge of how rock and metal behave at extreme pressures and temperatures helps. Each one removes versions of the collision that do not work. Eventually, perhaps, a much more precise picture will emerge. For now, we can reconstruct the broad sequence. Theia approaches. Gravity accelerates the encounter. The worlds make off-center contact. Shock waves move through their interiors, the mantles deform. Rock melts and vaporizes. Theia is disrupted. Its dense core material becomes associated with the surviving Earth. Rock from both bodies is thrown outward. Some escapes, some falls back, some remains in orbit. Earth spins rapidly beneath a hot cloud of debris. The separate planet called Theia no longer exists, but the collision has not finished producing consequences. In fact, the most recognizable consequence has barely begun. Around the battered Earth, countless pieces of silicate material now follow intersecting paths. Some are droplets of molten rock, some may be vapor, some are larger fragments. What remained around Earth after the collision was not yet a moon. It was a rapidly changing mixture of molten rock, vapor, droplets, fragments, and larger pieces of material moving around a planet that had itself been heated and reshaped by the impact. Some of that material had once belonged to Earth, some had belonged to Theia. By this point, those labels were becoming increasingly difficult to apply. A piece of silicate rock moving around Earth did not carry any obvious sign telling future scientists where it had come from. The collision had mixed material from both bodies, and the conditions surrounding the young Earth were hot enough that part of that material existed not as recognizable chunks of stone, but as liquid and vapor. This orbiting material is usually called the protolunar disk. The name makes it sound rather calm. A disk, something flat and orderly. Perhaps the sort of thing you could place neatly on a shelf. The actual environment would have been much less relaxing. Immediately after a giant impact, debris thrown into bound orbits does not begin as a perfectly smooth ring. Different pieces have different speeds, different orbital paths, and different temperatures. Some trajectories cross, material collides, some falls back toward Earth, some moves outward. Vapor expands around the planet while molten material gathers into streams, droplets, and clumps. Gravity begins organizing the mess, but gravity does not hurry. It simply keeps pulling. As orbiting material repeatedly interacts, its motion becomes more organized. Collisions between pieces remove some of the random movement. Material spreads into a broad disk around Earth's equatorial region. Models of lunar formation have long shown that a giant impact can create a circumterrestrial disk containing enough silicate material for the later growth of a large moon. If you had somehow been able to look at Earth from a safe distance, the planet would have been almost unrecognizable. There were no blue oceans, no white clouds floating over continents, no familiar moon nearby. Earth itself would have been glowing from heat released by the impact. Around it stretched a broad region of hot material. Some descriptions of the early disk use the image of a ring, which is useful, although it should not make us imagine something thin and solid like Saturn's rings today. The proto-lunar disk may have contained both silicate vapor and molten material, especially in its inner regions. The exact proportions depend on the energy of the impact, but thermal models describe a hot two-phase system in which vapor and liquid rock could coexist while the disk gradually cooled. Liquid rock is strange enough. Rock vapor requires a little adjustment. We're used to thinking of rock as the thing that remains stubbornly solid, while everything else melts, boils, freezes, or gets accidentally left in the oven. But rock is not permanently solid. Heat it enough and it melts. Heat it much further, and components of it enter the gas phase. The moon-forming collision was energetic enough for substantial melting and vaporization, meaning the environment around Earth could contain an atmosphere or disk region made partly from material that, under ordinary conditions today, would be part of the ground beneath your feet. Silicon, oxygen, magnesium, iron, sodium, potassium. Other elements present in rocky planetary mantles. At sufficiently high temperatures, many of these could participate in vapor above a layer of molten silicate. So there may have been a period when Earth was surrounded by something that could reasonably be described as rock weather. Not especially pleasant weather, but weather nonetheless. Vapor could cool and condense, molten droplets could collide, some material could vaporize again. Heat moved through the disk while radiation carried energy away into space. The disk was therefore not one fixed object. It evolved continuously. Near Earth, the situation was especially unusual because material encountered a limit imposed by Earth's gravity. This is where the Roche limit becomes important. The Roche limit is a distance inside which the tidal forces from a planet can prevent orbiting material from easily assembling into a large self-gravitating moon. Earth's gravity pulls more strongly on the near side of an orbiting object than on the far side. For an object far enough away, its own gravity can hold it together. Move too close to Earth, however, and the difference in Earth's pull across the object becomes increasingly important. A loosely held body can be disrupted. For silicate material around the early Earth, the relevant Roche distance is often placed at roughly 3 Earth radii from Earth's centre, although the precise value depends on assumptions about density and material behaviour. This created a kind of gravitational boundary in the proto-lunar disk. Outside the Roche limit, orbiting material could collide and remain together. A clump could attract nearby material. That made larger clumps. Larger clumps had stronger gravity. Eventually, the familiar runaway process of accretion could begin. Inside the Roche limit, things were more difficult. Material might collect temporarily, but Earth's tidal forces worked against the formation of a permanent large body. Instead of immediately becoming one moon, the inner disk remained spread out. That distinction is central to many traditional models of lunar formation. The outer disk can begin assembling moonlets, while the inner disk remains a hot, dense mixture of melt and vapor that evolves and spreads over a longer period. You can picture the Roche limit as a very strict building regulation. Outside this boundary, gravity says, yes, you may construct a moon here. Inside it, Earth says, absolutely not. Please put those rocks back. The rocks, unfortunately, have no planning department and continue orbiting anyway. The material inside the Roche limit still matters because disks naturally spread. Particles and fluid elements exchange angular momentum. Some material loses angular momentum and moves inward. Other material gains angular momentum and moves outward. This is a general feature of disks in astronomy. It happens in disks around young stars. It happens in rings around planets. It happened in the material surrounding the young Earth. The inner proto-lunar disk could therefore send material in two broad directions. Some moved toward Earth and was reaccreted. Some spread outward toward and eventually beyond the Roche limit. Once material crossed into the region where stable clumping became easier, it could join the growing moon. This means lunar formation was not necessarily a one-time sweep in which everything outside the limit instantly became the moon while everything inside vanished. The disk and the growing satellite interacted over time. Early numerical models showed that a large moon can accrete efficiently from an impact-generated disk, with its eventual mass depending on how much mass and angular momentum were present in the original debris. Later models made the process more detailed. The moon could begin growing mainly from material already beyond the Roche limit. Meanwhile, the inner disk would continue cooling and spreading. As material from the inner disk crossed outward, it could be captured by the growing moon. One study combining dynamical, thermal and chemical models estimated that material originating in the inner disk could eventually supply a substantial fraction of the moon's final mass, depending on the evolution of the system. This gives the ring around Earth a much more active role. It was not simply leftovers waiting to disappear. It was a reservoir, a changing supply of lunar material. And because different parts of the disk cooled at different rates, where material spent its early history may have affected its chemistry. The inner region was hotter. The outer region could cool and begin forming larger clumps sooner. Elements that are easily vaporized behaved differently from elements that remain comfortably inside molten rock. This is where the moon's unusual volatile composition becomes relevant. Lunar rocks are depleted in several volatile elements compared with Earth's mantle. Volatile elements are substances that more readily enter a gas phase under high-temperature conditions. The moon-forming impact and the hot disk provide an obvious environment in which volatile elements might behave differently from less volatile ones. But the details are more complicated than simply saying the collision boiled everything away. If volatile material entered the vapor phase but remained gravitationally bound to the Earth disk system, it did not necessarily escape into interplanetary space. It could condense again as the disk cooled. Researchers have therefore investigated how condensation, disk spreading, incomplete accretion, and liquid vapor separation could produce the volatile patterns measured in lunar samples. One proposed mechanism works because the growing moon eventually moves away from the disk. Early in the process, the inner disk is extremely hot and relatively poor in condensed volatile material. As it cools, increasingly volatile elements begin to condense. But if the moon's interaction with the disk causes its orbit to move outward before some of the more volatile material is efficiently delivered, that late condensing material can remain behind and eventually fall toward Earth instead. The moon would then end up depleted in those elements, even though the material had not necessarily escaped the Earth-Moon system entirely. Another line of evidence comes from isotopes of elements such as tin and potassium. Measurements of lunar samples have been interpreted as evidence that high-temperature liquid vapor processes occurred during lunar formation. Tin isotope work, for example, has been used to argue for equilibration and separation between liquid and vapor in a hot proto-lunar environment while the disk cooled. This is useful because an ancient disk leaves no photograph, it leaves chemistry. A tiny difference in isotope ratios measured billions of years later can tell scientists something about whether material condensed from vapor, separated from liquid, or experienced extreme temperatures. The detective work becomes almost absurdly precise. The original event involved planets colliding. The evidence may eventually come down to measuring minute differences in atoms inside a lunar rock smaller than your fist. Science often works that way. The universe does something enormously dramatic and then leaves behind paperwork in isotope ratios. The disk may also have helped address one of the most difficult questions we encountered earlier: why Earth and Moon material are so similar. If the initial debris contained different proportions of proto-Earth and Theia material, a sufficiently hot and mixed post-impact environment could allow chemical and isotopic exchange between the disk and the silicate atmosphere surrounding Earth. researchers have explored whether turbulent mixing and vapor exchange could reduce initial differences between the two reservoirs before the Moon fully assembled. That does not solve every isotopic problem automatically. Some elements exchange more easily than others. The timescale matters. The disk must remain hot and connected long enough. The chemical behavior of each element matters, and different giant impact models create different starting conditions. Still, the existence of a hot disk gives scientists a place where some of the original differences between Earth and Theia could have been reduced. The material was not simply thrown outward, frozen instantly, and left unchanged. It continued interacting. There may also have been much more structure in the debris than older simplified pictures suggested. Early simulations often treated the disk as a collection of many small particles. More recent high-resolution impact calculations can produce large clumps immediately after the collision. In some scenarios, substantial moon-like bodies can begin forming surprisingly quickly from material placed directly into distant orbit. That possibility changes the details of the story, but it does not remove the debris phase. Whether the Moon began as many smaller pieces gradually gathering, or as one or more large clumps produced rapidly by the impact, orbiting material still had to reorganize into a stable satellite. The exact route remains an active area of research, so rather than imagining one universally accepted sequence, it is safer to picture several versions of the same basic environment. Earth has been struck. A hot mass of silicate material surrounds it. Some material lies inside the Roche limit. Some lies outside. Some is molten. Some is vapor. Some may already exist in large fragments. Material falls back. Material spreads outward. Gravity continually rearranges everything, and beyond the Roche limit, objects start growing. At first, those objects may have been small. Two fragments collide and remain together. Another joins. The growing clump becomes massive enough to attract more material. Several clumps can form independently. They interact gravitationally. They collide with one another. Some merge. Others may be thrown onto different paths. Simulations of impact-generated disks have shown that this process can produce one dominant lunar body relatively quickly on astronomical timescales, in some classic models in less than a year after disk formation. Less than a year sounds astonishing, especially after spending several parts of this story casually moving through millions of years at a time. A planetary embryo can take millions of years to grow. The moon-forming collision may occur after tens of millions of years of solar system evolution. Then the actual assembly of a large satellite can proceed on a timescale that, in some models, would fit comfortably between two birthdays. Not that there was anyone around to celebrate, and even if a large moon formed quickly, its evolution was far from finished. The young moon would have been much closer to Earth than it is today. It would have been extremely hot. Its surface and interior would undergo further melting and differentiation. It would continue interacting with leftover disk material. Its orbit would evolve. Earth's rotation would evolve with it. The clean Earth-Moon arrangement visible today emerged only after an extended period of tidal and thermal change. But first, the material had to survive Earth's tides. That is why the Roche limit is such an important part of the story. A clump forming too close to Earth could be pulled apart again. A clump forming farther away could maintain itself. As these bodies grew, their own gravity became increasingly important. The largest embryo began to dominate the outer disk. It scattered smaller bodies. It absorbed others. Over repeated encounters, much of the available material became concentrated into one principal moon. There is nothing in physics that says the system must produce exactly one satellite immediately. Simulations can produce multiple moonlets. Some may collide. Some may temporarily coexist. Some may be lost. One study even proposed that the early Earth could have produced a companion moon alongside the main moon, with that smaller body surviving for millions of years before eventually colliding with the moon. That specific explanation was proposed partly to account for differences between the lunar near side and far side. although it remains one hypothesis among several. The important point is that a debris disk is not a machine that produces one perfect sphere on command. It is a gravitational system. Whatever bodies emerge depend on how much material exists, where it begins, how fast it moves, and how those bodies subsequently interact. There may have been several temporary arrangements before the final one. A moon begins growing. A smaller moonlet forms farther away. Two clumps merge. Another is broken apart. Material from the inner disk crosses the Roche limit. More debris falls back to Earth. The growing moon moves outward. The ring becomes less massive. Slowly, the space around Earth becomes less crowded. Much of the disk disappears not because its matter is destroyed, but because its material ends up in one of two places: Earth or the moon. Some fraction can escape, of course, but most of the important silicate mass in successful lunar formation models is redistributed within the Earth-Moon system. Theia is being divided again. First the planet was broken apart. Now the debris containing Theian and terrestrial material is being sorted between the surviving Earth and the developing Moon. If you could watch the process at high speed, the ring would gradually thin. The young Moon would become more distinct. Earth would remain incandescent below. The broad vapor structure would cool. Droplets and molten material would condense and settle. The system would begin looking slightly more familiar, only slightly. The early Moon would not be the pale grey object visible through a telescope today. It was hot enough for much of its exterior, and perhaps a very large fraction of its interior, to be molten. As accreting material struck its surface, additional impact energy would be converted into heat. Radioactive elements added more. Gravitational energy released as the Moon assembled also contributed. The result was a lunar magma ocean, a large-scale body of molten silicate from which the Moon's earliest crust and internal layers would eventually develop. Before we get there, however, the disk itself has one final useful lesson. It reminds us how misleading the phrase Theia created the Moon can be if taken too literally. Theia did not arrive with a moon hidden inside it, nor was the Moon simply a surviving piece of Theia knocked cleanly into orbit. The collision created a new environment containing material from the impactor and the proto-Earth. That material was heated, mixed, redistributed, condensed, spread, and reaccreted. The Moon emerged from those processes. Its birth was not simply destruction followed by a conveniently round leftover. It was destruction followed by planetary construction all over again. The same basic rules that built the planets from smaller material now began working around Earth on a much smaller stage. Collisions, gravity, accretion, heating, differentiation, orbital evolution. Only this time the raw material had already belonged to two larger worlds. The growing body beyond the Roche limit did not look much like the Moon we know today. There were no pale highlands, dark volcanic plains, sharp crater rims, or long shadows stretching across a quiet surface. The object forming from the debris around Earth was extremely hot, still accumulating material, and being struck repeatedly by fragments left over from the collision. Every new impact added mass, it also added heat, so a fragment falling onto the young Moon accelerated under lunar gravity. When it struck, much of its kinetic energy became heat. Multiply that process across an enormous number of impacts, combine it with the heat already inherited from the Moon-forming collision, and add the energy released as a planetary body assembled under its own gravity, and the result was a Moon that was probably extensively molten. The familiar grey world had begun with a magma ocean. Apollo samples provided some of the first major evidence for this. When scientists examined the returned rocks, they found ancient minerals and rock types whose chemistry suggested that the Moon had once experienced large-scale melting and differentiation. Later orbital measurements revealed widespread northocite, a light-coloured rock rich in plagioclase feldspar across the lunar highlands. That broad distribution is one of the strongest reasons scientists think much of the early Moon was covered by a deep magma ocean. Calling it an ocean can create the wrong mental picture. There were no waves rolling onto beaches, no rain, no small volcanic island offering refreshments. The ocean was molten silicate rock, possibly hundreds or even more than 1,000 kilometers deep in some models. Depending on how completely the moon melted during accretion, much of the body may initially have behaved as a vast reservoir of liquid rock beneath a hot surface. The temperature would have been high enough for the moon to glow. Above the magma, there may have been an atmosphere produced partly from vaporized rock and other volatile materials. As the moon radiated heat into space, that atmosphere and the molten surface began changing rapidly. Space is cold, but cooling a planetary body is not as easy as leaving a cup of tea on the kitchen counter. The outermost material loses heat first. Material underneath remains hot. If a crust forms, it can act as insulation, reducing the rate at which the deeper interior loses energy. Convection inside molten rock also transports heat. Radioactive elements continue releasing additional energy, and during the earliest period, impacts keep delivering more. So the moon did not simply turn from molten to solid overnight. Its cooling became a long geological process. Exactly how long the lunar magma ocean persisted remains debated. Different dating methods and thermal models give different histories, partly because later impacts and magmatic events can reset some of the clocks preserved in lunar minerals. Research on ancient zircon and anorthosite has placed important constraints on the process, while newer work continues to revisit whether some lunar ages record original magma ocean crystallization or later episodes of heating and remelting. The basic sequence, however, is easier to understand. As the molten moon cooled, minerals began crystallizing. Not all minerals crystallize at the same temperature, nor do they all have the same density. Early in the cooling process, minerals rich in magnesium and iron, including olivine and pyroxene, could begin forming within the magma. These minerals were generally denser than the surrounding liquid. Rather than floating to the surface, they tended to sink. Over time, they accumulated in deeper layers. The moon was beginning to separate itself internally. A mantle was developing. This is planetary differentiation happening again. The original dust around the sun had gathered into planetesimals. Planetesimals had gathered into embryos. Earth and Theia had differentiated into cores and mantles. Then the impact destroyed and mixed part of that structure. Now the moon, assembled from the aftermath, was sorting itself into layers of its own. The process did not produce perfectly neat geological stripes. Real magma is chemically complex. Crystals interact. Convection moves material. Some layers can become unstable. Later melting alters earlier structures. But the overall tendency is clear enough. Dense minerals move downward. Lighter materials can move upward. And one mineral in particular became extremely important for the future lunar surface: plagioclase feldspar. As crystallization progressed and the composition of the remaining magma changed, large amounts of calcium-rich plagioclase began to form. Unlike many of the minerals crystallizing earlier, plagioclase was relatively buoyant in the remaining lunar melt. So it floated. Individual crystals rose toward the surface. More crystals joined them. Over time, they accumulated into a thick, light-coloured crust. This process is the standard explanation for the ancient anorthositic crust of the lunar highlands, although researchers continue refining how efficiently flotation occurred and whether the magma ocean behaved as a completely liquid body or, during some stages, as a crystal-rich slush. Experimental and geophysical work shows that the details of crust formation remain an active subject, even while the broader connection between plagioclase-rich crust and early lunar differentiation is well established. That means the bright areas you can see on the moon today are connected to this ancient separation process. Look at a full moon, and the lighter regions are the lunar highlands. They are heavily cratered and extremely old. Much of their underlying crust is rich in anorthositic material. The rock exists because crystals once formed inside a molten young moon, and moved upward because they were less dense than the liquid surrounding them. It is an unusually direct link between something visible from your garden and mineral physics operating more than 4 billion years ago. The darker areas came later. Those broad grey patches, historically called maria, are enormous plains created mainly by basaltic lava that filled large impact basins much later in lunar history. Early observers once thought they might be seas, which explains names such as Mare Imbrium, the Sea of Rains, and Mare Tranquillitatis, the Sea of Tranquility. There was no actual ocean in the Sea of Tranquility. Astronomers had simply looked at a dark patch from several 100,000 kilometers away and made a reasonable guess. We have all done worse with things much closer. The first crust forming over the magma ocean would also have looked very different from the battered highlands visible today. It had not yet accumulated billions of years of craters. Large impacts would soon begin breaking, excavating, melting, and rearranging it. Some sections of the early crust may have been destroyed entirely. Others were buried beneath ejecta. Material from deep inside the moon could be thrown upward by later impacts, giving modern scientists access to rocks that originated far below the ancient surface. That is one reason lunar impact basins are scientifically useful. A sufficiently large collision is inconvenient for the moon, but very helpful for geologists several billion years later. It performs excavation without asking for funding. While the crust was developing, the last portions of the magma ocean became chemically unusual. When a crystal forms, some elements fit easily into its mineral structure. Others do not. The elements that do not fit remain concentrated in the liquid. As more and more of the magma crystallizes, those reluctant elements become increasingly concentrated in the final remaining melt. Among them were potassium, rare earth elements, phosphorus, uranium, thorium, and other heat-producing or chemically incompatible elements. Lunar scientists often refer to one important component of this late-stage material as KREEP, an acronym built from potassium, represented by K, rare earth elements, REE, and phosphorus, P. KREEP is a much easier thing to say than potassium, rare earth element, and phosphorus-rich lunar material every 5 minutes, which may be one of geology's kinder naming decisions. This late material became important in the moon's later volcanic evolution because it contained elements capable of producing heat through radioactive decay. The crystallization of the magma ocean therefore did more than create crust and mantle. It produced chemical layering that would influence what happened inside the moon for a very long time afterward. Ancient lunar samples support this general sequence in which early olivine and pyroxene-bearing materials were followed by plagioclase-rich crustal rocks and late melts enriched in incompatible elements. The interior may then have become unstable. Crystallization sorts materials according to mineral chemistry, but it does not always arrange them in the most gravitationally comfortable order. Some relatively dense late-forming minerals can end up above lighter material. When that happens on a large enough scale, gravity eventually starts correcting the arrangement. Dense material sinks, lighter material rises. The lunar mantle may have experienced this kind of overturn after much of the magma ocean solidified. Parts of the newly formed mantle could descend while others moved upward, producing additional melting and changing the chemistry of the interior. Modern models of magma ocean crystallization investigate how such overturn could have modified or even partly removed the original layering produced during solidification. So even after the moon had assembled into one main body, it remained active internally. Formation had not finished simply because the debris stopped behaving like a ring. The new moon still had to cool, its crust had to form, its mantle had to reorganize. Its orbit was changing at the same time, and Earth was changing with it. The early moon formed much closer to Earth than the average distance of about 384,000 kilometers that separates the two bodies today. The exact starting distance depends on the formation model, but the moon had to begin outside the region where Earth's tides would prevent it from remaining intact. From there, gravitational interaction between the two bodies began gradually altering their motion. The basic mechanism comes from tides. The moon's gravity pulls on Earth. Today, its most obvious effect is the rising and falling of the oceans, but tides also deform the solid Earth. Early Earth was hotter, rotating faster, and had a very different surface, so its tidal response was not identical to the modern one. The important point is that Earth rotated faster than the Moon orbited. The tidal deformation raised by the Moon therefore did not remain perfectly aligned with the line between the two bodies. Because Earth was rotating, the tidal bulge was carried somewhat ahead. That offset allowed Earth's gravity to exert a torque on the Moon. Angular momentum was transferred from Earth's spin into the Moon's orbit. Earth's rotation gradually slowed. The Moon moved outward. This process continues today, although the rate has varied enormously through time because tidal dissipation depends on the physical state of Earth, the arrangement of oceans, continental geometry, lunar distance, and other factors. Long-term models therefore do not simply take the modern recession rate and run it backward at a constant speed. In the beginning, though, the Moon would have appeared enormous in Earth's sky. Not because the Moon itself was necessarily much larger than it is now, but because it was much closer. Its apparent size would have been dramatic. If there had been someone standing safely on an already solid part of Earth, which is doing a considerable amount of work in that sentence, the young Moon could have dominated the sky. Earth would have looked even more extraordinary from the Moon. The two bodies were physically connected through tides in a much stronger way than they are now. The closer two bodies are, the stronger tidal effects become. The early Moon therefore experienced substantial deformation. Its shape responded to Earth's gravity. Tidal forces also generated heat inside it. As the Moon's orbit and rotation evolved, those forces could contribute additional energy to an interior already trying to cool. Recent work has even proposed that strong tidal heating may have caused widespread remelting around 4.35 billion years ago, potentially resetting the ages recorded by many lunar rocks and helping reconcile different estimates for the Moon's formation age. That interpretation remains an active research topic, but it demonstrates how strongly orbital evolution and geological evolution can be linked. The Moon's rotation was changing as well. Today, the Moon rotates once during each orbit around Earth. That is why the same hemisphere generally faces us. It is not because the Moon does not rotate. If it did not rotate at all, we would eventually see every side as it travelled around Earth. Instead, one rotation per orbit keeps nearly the same face pointed toward us. This state is called synchronous rotation, or tidal locking. The young Moon probably did not begin in precisely this state. Earth's tidal forces acted on it over time, changing its spin until the rotation became synchronized with the orbit. Once that happened, the arrangement became stable. The Moon acquired a permanent near side and far side relative to Earth, not a dark side. Both sides receive sunlight. The far side merely has the misfortune of being the side Earth rarely gets to look at directly, which is probably why it has avoided a great deal of unsolicited commentary. The distinction between the two hemispheres eventually became much more than a matter of visibility. The near side has thinner crust on average, and contains most of the large dark basaltic plains familiar from Earth. The far side has generally thicker crust and far less mare volcanism. Explaining that difference is still an important problem in lunar science. Some proposed explanations involve the asymmetric distribution of heat-producing elements. Others involve the effects of Earth on the hot early Moon. Large impacts also contributed, and samples returned from the far side by China's Chang'e 6 mission are now providing direct information from a region scientists previously knew, mainly through remote sensing. A 2026 analysis of Chang'e 6 anorthosite fragments found important similarities with near-side Ferroan anorthosites, supporting a broadly comparable magma ocean-derived primary crust on both hemispheres, before later processes produced much of the difference we see today. That is an important reminder not to imagine the modern lunar surface appearing immediately after formation. The first crust was only a starting surface. The Moon we recognize was built on top of it through billions of years of impacts, volcanism, cooling, crustal modification and orbital evolution. Some of its largest basins would not exist until hundreds of millions of years later. The Dark Maria would not be filled with lava until later still. The fresh-looking rays around younger craters such as Tycho are enormously younger than the Moon itself. The Moon has an early history, a middle history, and comparatively recent geological events, even though recent on the Moon can mean something happened before the first dinosaurs appeared on Earth. For the moment, the newborn Moon was mainly a hot differentiated body moving away from a hotter young Earth. The disk that had supplied its material was fading. Material inside the Roche limit either spread outward, joined the Moon, or fell back onto Earth. Large remaining fragments were swept up or scattered. The space between the two bodies gradually became cleaner. One dominant satellite remained. The Earth-Moon system had begun settling into a form that could persist. But even now, calling the Moon a finished product would be premature. Its magma ocean continued crystallizing. Its crust continued evolving. Its interior continued moving. Its orbit continued expanding. Impacts continued arriving from the unsettled solar system. The Earth below it was cooling as well, rebuilding an atmosphere and eventually developing surface conditions very different from those immediately after the collision. The two worlds were no longer simply the survivors of a catastrophe. They had become a gravitational pair, and the pair began changing one another. Every tide transferred energy. Every small change in Earth's rotation affected the Moon's orbit. Every increase in lunar distance slightly altered the strength of the interaction. Over billions of years, those tiny exchanges accumulated into enormous differences. The Moon moved from a close orbit to its modern distance. Earth's day became much longer than it had been shortly after the impact. The Moon became tidally locked. Its interior cooled. Its once global molten exterior disappeared beneath solid crust. The violent debris surrounding Earth became a single companion that could remain for billions of years. Yet something curious had happened during that transformation. The Moon had formed from material whose original identities were now mixed together. Some came from the proto-Earth. Some may have come from Theia. The proportions remain one of the central questions in the entire story. If you picked up an ancient lunar rock and could somehow trace every atom back to the moment before the impact, part of it might lead you to Earth. Another part might lead you to a planet that no longer exists. And the deeper scientists look into lunar chemistry, Earth's mantle, and simulations of the collision, the more important that Vanished Planet becomes, because creating the Moon did not necessarily use all of Theia. Its core had gone somewhere. The rest of its mantle had gone somewhere. After the Moon had taken shape, Theia was nowhere to be seen. There was Earth. There was the new Moon. There was gradually less debris surrounding them, but the planetary body that had existed independently before the collision was gone. This raises an obvious question. Where did it go? The simplest answer is that Theia went almost everywhere. Its material was divided between several destinations. Some probably became part of the Moon. A large amount entered Earth. Its metallic core was largely incorporated into Earth's interior. Some rocky material may have remained chemically distinct inside Earth's mantle. A smaller amount of impact debris may have escaped the Earth-Moon system completely. Theia disappeared as a planet because the organized structure that made it a planet was destroyed. Its atoms were another matter. Atoms are much harder to get rid of. When two planets collide, matter does not simply vanish, because the collision is energetic. Rock may melt, metal may separate, material may vaporize, pieces may be thrown into space, chemical compounds may break apart and recombine, but the basic material remains. Theia therefore did not disappear in the same way a candle flame disappears when it is extinguished. A better comparison would be taking a large building apart and using the materials in several new structures. The original building is gone, its bricks are not. Of course, the collision between Earth and Theia involved slightly more pressure than an average renovation. The first major destination for Theian material was Earth itself. In most giant impact scenarios, Earth remains the dominant body after the collision. Theia is disrupted, and much of its mass becomes gravitationally bound to Earth. Some of that material is deposited relatively close to the surface or mixed into the mantle. Dense material behaves differently. If Theia had differentiated before the collision, it possessed a metallic core containing a large amount of iron and other dense elements. Earth already had a metallic core of its own. When Theia struck, those two cores were brought into the same planet. Impact simulations and physical models indicate that the impactor's metallic core could descend through Earth's silicate material and merge with Earth's protocore on relatively short timescales. In many giant impact calculations, the metallic cores of the proto-Earth and Theia combine within hours of the collision, although the details of how much metal chemically equilibrates with surrounding silicate material remain important and complicated. It would not have looked like one neat iron sphere sinking through another neat sphere. Theia's core could have been stretched and deformed during impact. Metal could break into streams and droplets. Some regions might interact strongly with molten silicate. Other portions might remain relatively coherent. The behavior depends on the collision angle, temperature, pressure, impactor size, and physical state of the two planets. There is even experimental and modelling work suggesting that a giant impact can leave chemical or structural layering near the top of Earth's core as the incoming metallic material merges with the existing protocore. So deep beneath us, some portion of Earth's core may contain metal that once belonged to Theia. There is no useful way to point at one region of the modern core and say, that bit over there is definitely Theia. Earth's core has had more than 4 billion years to evolve. Its outer portion is liquid. Material moves. Heat escapes. The solid inner core has grown over time. The entire system is dynamic. Any Theian metal that entered it would have become part of Earth's core evolution. But from a mass balance point of view, it had to go somewhere, and downward was the natural destination for dense metallic material. This creates one of the stranger consequences of the collision. Part of the planet that created the moon may now be roughly 3,000 kilometers beneath your feet, not in recognizable pieces, not as an underground miniature planet, but incorporated into the central structure of Earth. The rocky mantle of Theia had a more complicated fate. Some of it entered the debris that contributed to the moon. Some was probably mixed into Earth's mantle, and this is where a major scientific question appears. How thoroughly did the impact mix the two worlds? It is tempting to imagine a planetary collision as a giant blender. Everything is melted, everything is stirred. Theia and Earth become completely homogeneous. Problem solved. Actual simulations suggest it is not necessarily that simple. Research on the thermal state of Earth after the moon-forming impact indicates that much of Earth's mantle could have been melted, while the degree of physical mixing depends strongly on the impact scenario. In standard giant impact calculations, substantial portions of the mantle may remain incompletely mixed, even while experiencing extensive melting. More energetic alternative impact models can produce much stronger mixing. Melting and mixing are not the same thing. You can melt two materials without instantly distributing every part of one uniformly through the other. Imagine adding cream to coffee. Before stirring, both are liquids. That does not mean the cup is immediately uniform. Now imagine the cup is several thousand kilometers deep and rotating rapidly, while portions of it are being thrown into orbit. The comparison becomes less useful fairly quickly, but the distinction survives. If the standard giant impact did not completely homogenize Earth's mantle, then pieces of the pre-impact Earth and pieces of Theia might have retained some chemical identity. The upper portions of Earth's mantle would undergo enormous amounts of later circulation. Hot material rises, cooler material sinks. Partial melting produces magma. Plate tectonics eventually carries surface material downward and brings mantle-derived magma upward. Given billions of years, you might expect most ancient distinctions to become thoroughly blurred. Much of them probably did. But Earth's mantle may not mix as perfectly as a pot of soup. Large chemically distinct reservoirs can potentially survive for extraordinarily long periods, particularly in the deep mantle. and sitting near the bottom of Earth's mantle are two enormous structures that have attracted a great deal of attention. One lies broadly beneath Africa, the other lies beneath the Pacific Ocean. They are called large, low-velocity provinces, usually shortened to LLVPs. We cannot see them directly. No drill can reach anything remotely close to that depth. Instead, scientists detect them using earthquakes. When an earthquake occurs, seismic waves travel through Earth. Their speeds and paths depend on the properties of the material they pass through. By recording those waves at many locations around the planet, seismologists can build three-dimensional pictures of structures deep underground. It is a little like performing a medical scan on the entire Earth, except the machine is made from earthquakes, and the patient refuses to fit inside the hospital. The LLVPs stand out because seismic waves travel through them differently from the surrounding mantle. They're enormous. Their horizontal dimensions are measured in thousands of kilometers. They rise hundreds of kilometers above the core mantle boundary in places. Researchers have long debated what they are made from and why they exist. Then scientists asked a particularly interesting question. Could they contain Theia? A 2023 study combined giant impact simulations with calculations of mantle convection and proposed that substantial pieces of Theia's mantle could have survived the collision and been deposited inside Earth's lower mantle. If Theia's mantle material was roughly 2 to 3.5% denser than the surrounding proto-Earth mantle, the simulations showed that large blobs could gradually sink and collect above Earth's core, eventually producing structures resembling the observed LLVPs. That possibility received considerable attention for an understandable reason. If correct, we may have found part of a destroyed planet inside our own, but this needs careful wording. Scientists have not established that the LLVPs definitely are Theia. The LLVPs are observed structures. Their interpretation as remnants of Theia is a hypothesis. There are other models for their origin, including processes involving Earth's own mantle differentiation and long-term internal evolution. So it would be premature to say we have discovered Theia sitting beneath Africa and the Pacific. What the 2023 work demonstrated is that a physically plausible giant impact scenario can place dense Theian mantle material deep inside Earth, and that mantle convection models can preserve such material for billions of years in structures similar to the LLVPs. That is already remarkable. The impact happened around 4.5 billion years ago. Earth's mantle has been moving ever since. Continents have assembled and broken apart. Oceans have opened and closed. Material has risen toward the surface and sunk again. Entire mountain ranges have appeared and eroded away. And yet, if the hypothesis is correct, pieces of Theia on scales of tens of kilometers could have survived the initial impact and later accumulated deep enough to remain partially isolated from the rest of Earth's mantle. That would make the LLVPs something like geological storage areas from the birth of the Earth-Moon system. Extremely inaccessible storage areas. If you misplaced your keys down there, it would probably be best to have another set made. The density difference proposed in the model is also interesting. The researchers connected it partly to differences in iron oxide content between the mantles involved in the collision. A mantle containing somewhat more iron can be denser. The Moon itself appears to contain more FeO in its mantle than Earth's bulk silicate mantle, and that difference can be used to constrain possible compositions for Theia. The 2023 model used these relationships to estimate that Theian mantle material could have been dense enough to sink toward the bottom of Earth's mantle, rather than remaining uniformly distributed. If that happened, the aftermath of the collision becomes surprisingly organized. Theia's dense metallic core goes down toward Earth's core. Some relatively dense pieces of Theia's rocky mantle also migrate downward, although they stop above the metallic core because they are still silicate rock. Other Theian mantle material mixes into Earth's mantle. Still more enters orbit and contributes to the Moon. One lost world becomes several different parts of a new planetary system. There is another destination we should not forget. Space. Not every fragment thrown outward by the collision had to remain gravitationally attached to Earth. Some material would have received enough energy to escape. Once outside Earth's gravitational control, those fragments could enter independent orbits around the Sun. For a time, the inner solar system may have contained pieces produced directly by the moon-forming event. Some might later collide with Earth again. Some could strike Venus. Some could reach asteroids. Others might eventually fall into the Sun or be scattered onto different trajectories. Calculations of moon-forming ejecta have suggested that escaping fragments could interact with other bodies in the solar system, while reviews of lunar chronology note that any surviving giant impact ejecta would now be extraordinarily difficult to identify, because most material was reaccreted by Earth and the Moon, or otherwise dynamically dispersed. So somewhere in the ancient solar system, there may once have been small pieces of Theia travelling alone after their parent world had ceased to exist. Whether any recognisable fragment survives today is another question entirely. Finding one would be extremely difficult. Meteorites are already challenging to trace back to specific parent bodies unless they have distinctive compositions. A fragment derived from the moon-forming collision would have spent billions of years exposed to further impacts and orbital evolution. And if Theia formed from material chemically similar to Earth, identifying a small fragment as definitively Theian would be even harder. You would first need a clear idea of Theia's chemical fingerprint. Unfortunately, determining Theia's fingerprint is exactly the problem scientists are trying to solve. The search becomes slightly circular. To find Theia, you need to know what Theia looked like chemically. To know what Theia looked like chemically, it would be very helpful to find Theia. Planetary science occasionally has this sense of humour. Fortunately, the Moon provides a much larger sample. In the canonical giant impact model, a significant fraction of the material placed into lunar orbit comes from the impactor. Some isotopic studies have argued that the Moon could contain a very large contribution from Theia, if Theia and the proto-Earth formed from a common isotopic reservoir in the inner solar system. A 2021 vanadium isotope study, for example, found results compatible with a canonical impact in which roughly 80% of lunar material came from the impactor, while Earth and Theia had originally accreted from broadly similar material. Other measurements and impact models can favour different proportions. That is why you will sometimes encounter apparently conflicting claims. One explanation says the Moon is mostly Theia. Another says it contains much more Earth material. Another emphasises extensive post-impact mixing. Another starts with an Earth and Theia that were already isotopically similar. These models are trying to satisfy the same difficult collection of observations. The exact fraction of Theia inside the Moon is not settled, but almost every giant impact scenario leaves the same broad conclusion. A meaningful amount of the lost planet probably survived there. Every lunar sample may therefore contain some mixture of two ancient worlds. A rock collected by an Apollo astronaut could include atoms that were part of the proto-Earth and atoms that were part of Theia before the collision. They have been together so long that separating their histories is difficult. That is why isotope measurements have to be so precise. Scientists are looking for tiny differences preserved after extraordinary amounts of heating and mixing. Some elements are especially useful because their isotopic ratios vary among different solar system materials. Oxygen, titanium, chromium, tungsten, zirconium, vanadium. Each provides a slightly different constraint. Studies using several of these systems have shown that Theia cannot simply be assigned any convenient composition. Its chemistry has to be compatible with the measured similarities and differences between Earth's mantle and lunar rocks. This chemical reconstruction has produced an interesting picture. Theia may not have been an exotic visitor from a completely different part of the solar system. It may have formed from broadly similar inner solar system material to Earth. That would help explain why mixing material from the two bodies did not leave the Moon with an obviously foreign isotopic signature. But similar does not mean identical. Small differences could still exist. Those differences are potentially the fingerprints scientists need. And if researchers become better at identifying which parts of the Moon came preferentially from the impactor, lunar rocks could tell us more about Theia than Earth itself can. Earth is difficult because it has spent billions of years processing its interior. The Moon is quieter. Its ancient rocks have been disturbed by impacts, volcanism, and thermal events, but it lacks Earth's plate tectonic conveyor belt. Some lunar material may therefore preserve information that Earth erased. This gives Theia an unusual sort of afterlife. Its surviving material may be easiest to study on a different world. The planet hit Earth, disappeared, helped create the Moon, and then left some of its most accessible evidence hundreds of thousands of kilometers above Earth, rather than beneath the ground where the collision occurred. And we have already brought pieces of that evidence home. Apollo astronauts returned hundreds of kilograms of lunar material. Soviet robotic missions returned smaller samples. More recently, China's Chang'e missions have added samples from regions not represented in the Apollo collection. Every new sample gives scientists another opportunity to test the details of lunar origin. The more varied the sampling locations, the better the chance of finding material that preserves different parts of the Moon's interior and early history. Some lunar rocks have undergone extensive later melting. Others represent ancient crust. Some may contain material excavated from deeper layers by large impacts. If different regions contain slightly different proportions of proto-Earth and Theia material, those differences could eventually help reconstruct the impact itself. Theia may therefore be lost, but it is not entirely inaccessible. We simply have to recognize it inside things that have different names now. Earth, the Moon, possibly the deepest mantle, possibly Earth's core, perhaps scattered remnants elsewhere in the solar system. There is no single location where Theia went, because the collision ended the very thing that made one location meaningful. Before impact, Theia's material was held around one center of gravity. After impact, it was distributed among several reservoirs. That is the disappearance. Not annihilation, redistribution. If you could somehow collect every atom that belonged to Theia immediately before the collision, and mark it with a tiny label, then watch the next 4.5 billion years at high speed, those labels would spread. A huge collection would move into Earth. Some would sink. Some would remain in the mantle. Some might later rise again through mantle circulation. Another large collection would become incorporated into the Moon. Some would escape. Some might return. Over geological time, Theian atoms incorporated into Earth's mantle could participate in melting. Material could eventually contribute to volcanic rocks. Those rocks could weather. Their elements could enter sediments. Some could be recycled back into the mantle. Once a planet is mixed into another active planet, its material becomes part of that world's geological system. This makes an amusing question surprisingly difficult. Are we standing on Theia? Perhaps, in a very limited chemical sense. The crust beneath you is not likely to be a preserved slab of Theia's ancient surface. Earth's earliest crust has been overwhelmingly reworked. But if some of Theia's mantle mixed into Earth's mantle after the giant impact, then portions of that material have had billions of years to circulate through the planet. It is possible that some atoms originally delivered by Theia have since reached Earth's upper layers. Tracing a specific atom back to Theia would be effectively impossible. It may have had a very busy 4.5 billion years. Still, the larger point holds. Modern Earth is not simply the proto-Earth with a moon added beside it. The impact changed Earth's composition as well. This surviving planet is partly the product of both worlds, and that may be the best answer to what happened to Theia. It became difficult to separate from Earth. It became difficult to separate from the Moon. It may even be hiding in giant structures at the bottom of Earth's mantle. The lost planet did not leave behind a corpse floating through space. It left behind a planetary system, which means the evidence for Theia has been sitting in front of us all along. We see one part when the Moon crosses the night sky. We live on another part. And if scientists want to determine whether those fragments truly preserve the chemical and physical signature of the missing world, what do they need to do beyond simply telling a plausible impact story? They have to reconstruct one from evidence that has been heated, melted, buried, blasted into space, mixed into another world, and left alone for more than 4 billion years. which is not the easiest investigation anyone has ever been given. There was no camera pointed at Earth when Theia arrived. There was no instrument measuring the impact speed. No one recorded the angle. No convenient piece of Theia remained floating nearby with an identification number attached to it. Instead, scientists had to begin with the objects that exist today and ask what kind of event could have produced them. Earth, the Moon, their masses, their compositions, their internal structures, their rotation and orbital motion, the chemistry of lunar rocks, even the elements that are missing from those rocks. Each one places limits on what could have happened. The giant impact idea became successful, not because one piece of evidence suddenly announced that Theia had struck Earth, but because several independent clues began pointing toward the same general kind of event. And the first major collection of clues arrived in boxes from the Moon. Between 1969 and 1972, 6 Apollo missions landed astronauts on the lunar surface and returned hundreds of kilograms of rocks, soil, dust, and drilled material to Earth. Before those samples arrived, theories about the origin of the Moon had to rely mainly on astronomy, orbital mechanics, and observations made from a distance. After Apollo, scientists could place pieces of the Moon inside laboratories. They could measure the minerals, they could date them, they could heat them, crush them, dissolve tiny portions of them, separate individual elements, measure isotopes with extraordinary precision. The Moon had gone from something people looked at through telescopes to something scientists could place under a microscope, and it immediately became more complicated. The lunar samples showed that the Moon is made largely from the same broad kinds of silicate materials found in Earth's rocky mantle. They also supported the idea that the young Moon had undergone extensive melting and differentiation, including the formation of the magma ocean we followed earlier. But one feature became especially important for the question of where the Moon came from. In many isotope systems, Earth and the Moon are extremely similar. Isotopes are different versions of the same element. Every oxygen atom, for example, has 8 protons. But oxygen atoms can contain different numbers of neutrons. Oxygen-16 has 8 neutrons. Oxygen-17 has 9. Oxygen-18 has 10. The chemistry remains oxygen chemistry, but the relative abundance of those isotopes can vary slightly between planetary bodies. Those small differences are enormously useful. Different objects formed from different mixtures of material in the early solar system. Meteorites from Mars, asteroids, and other sources can carry distinctive isotope ratios. In effect, isotope measurements give planetary scientists a way to compare chemical fingerprints. Not fingerprints in the detective film sense where someone dusts the Moon and finds Theia's thumbprint. Much more inconvenient fingerprints involving mass spectrometers and numbers with several decimal places. When lunar oxygen was compared with terrestrial oxygen, researchers found an extraordinarily close resemblance. That was surprising. If the Moon had formed elsewhere in the solar system and had simply been captured by Earth, it should probably have retained a more obviously independent chemical identity. Mars does. Many meteorite parent bodies do. Different parts of the solar system are not isotopically interchangeable, yet the Moon looked remarkably Earth-like. For years, some measurements found Earth and Moon oxygen to be essentially indistinguishable within experimental precision. More recent high-precision analyses have reported a small but measurable difference, with deeper derived lunar materials potentially preserving a somewhat different oxygen isotope composition from surface-derived rocks. That result has been interpreted as possible evidence that the impactor and proto-Earth were similar, but not perfectly identical. That tiny distinction is important. If Earth and Moon were absolutely identical in every relevant isotope, scientists would need to explain how a Moon made partly or mostly from another body ended up chemically indistinguishable from Earth. If they are slightly different, then some trace of the impactor may have survived the mixing. Either way, the measurements constrain Theia. The impactor cannot simply be given any composition we like. Its chemistry has to produce the Moon we actually have. Oxygen was only the beginning. Researchers examined titanium, chromium, zirconium, silicon, tungsten, vanadium, potassium, and many other elements. Some showed very close Earth-Moon similarities, others revealed small but significant differences. Together, those measurements became one of the toughest tests for every model of lunar formation. Tungsten provides a particularly useful example because its isotopes are connected to the earlier stages of planetary differentiation. One isotope, tungsten-182, is produced through the radioactive decay of hafnium-182. Hafnium-182 existed only during the early solar system because it has a relatively short radioactive lifetime on planetary timescales. Hafnium and tungsten also behave differently during core formation. Hafnium prefers silicate rock. Tungsten is more willing to enter metal. So when a young planet separates into a rocky mantle and metallic core, the hafnium-tungsten system can preserve information about when that separation happened. This makes tungsten a kind of early planetary clock, not the sort you would want beside the bed. The display would be extremely difficult to read. High-precision measurements of lunar tungsten found that the modern Moon has a small tungsten isotope difference from Earth's present mantle. Researchers concluded that much of this difference can be explained by Earth receiving more additional material than the Moon after the moon-forming event, a process known as late accretion or the late veneer. When that later contribution is accounted for, Earth and Moon appear to have been much more similar in tungsten immediately after lunar formation. That creates another challenge. A traditional giant impact often produces a moon containing a large amount of Theia. If Theia had developed a tungsten isotope composition significantly different from Earth's, the Moon should preserve more of that difference. Some dynamical and geochemical modelling has found that producing the observed Earth-Moon tungsten similarity through a conventional impact between independently evolving bodies can be statistically difficult. Other measurements offer another route. Vanadium isotope data published in 2021 were interpreted as compatible with a more traditional impact in which roughly 80% of lunar material could come from Theia, provided that Theia and the proto-Earth had accreted from broadly similar material in the inner solar system. This is a good example of how the investigation actually works. One measurement does not settle the entire story. A new isotope result changes the acceptable range of models. Another element provides a different constraint. A computer simulation is run again. A model that looked promising fails one chemical test. Another succeeds chemically, but produces too much angular momentum. A third creates the correct moon mass, but puts too much metallic iron into orbit. Scientists then adjust the assumptions and try again. It is less like discovering one dramatic clue and more like attempting to solve a very complicated crossword in which gravity has filled in half the boxes and chemistry refuses to explain its handwriting. The Moon's iron content gives another major clue. Earth possesses a very large metallic core. The Moon does not. Modern measurements of lunar rotation, gravity, seismic behaviour and laser ranging indicate that the Moon does contain a metallic core, including a fluid component, but that core represents only a small fraction of the Moon's total mass. One analysis using lunar laser ranging constrained the lunar core mass fraction to roughly 1.6 to 1.8%. That matters because different moon formation theories predict different internal compositions. Suppose Earth and the Moon had simply formed independently from similar material in the same region of space. Why would one end up with such a large proportion of metal and the other with so little? Suppose the Moon were captured intact from somewhere else. Again, we would need to explain its unusual relationship with Earth's composition and its small core. A giant impact offers a natural mechanism for preferentially placing rocky mantle material into orbit, while leaving most dense metallic material with Earth. In the traditional picture, both proto-Earth and Theia have differentiated. Each has a metallic core and rocky mantle. During an off-center impact, much of the material placed into orbit comes from the outer silicate portions of the two bodies. The iron-rich cores are more likely to remain with the largest surviving planet. Computer simulations published by Robin Canup and Eric Asfag in 2001 showed that an oblique collision involving a roughly Mars-sized impactor could produce an iron-poor satellite with approximately the Moon's mass, while also matching an important dynamical constraint: the angular momentum of the Earth-Moon system. Angular momentum is where the evidence becomes less chemical and more orbital. Earth spins. The Moon travels around Earth. Those motions contain angular momentum. Tides have redistributed that angular momentum between Earth's rotation and the Moon's orbit over billions of years, but the total amount provides a powerful clue about the system's beginning. A proposed collision cannot simply create a nice-looking moon. It has to produce the right kind of motion. Imagine reconstructing a billiard shot after walking into the room long after the balls have stopped moving. If you know where the balls began, where they ended, their masses, and how momentum behaves, you can eliminate many possible shots. The Earth-Moon problem is considerably worse because the billiard balls are planets, and the table has been changing for 4.5 billion years. Still, the principle is similar. The Moon is unusually large relative to its planet. Its orbital angular momentum is substantial. Earth rotates in the same general direction as the Moon orbits. A successful origin theory has to explain those properties together. The giant impact model does this rather naturally, because an off-center collision can transfer rotational motion into the combined system. Where the impact occurs matters. How fast Theia is moving matters, the direction matters, the mass ratio matters. A direct collision and a glancing collision produce very different angular momenta. This is one reason scientists can use the modern Earth-Moon system to estimate what an event billions of years ago may have looked like. The present motion contains a memory of the impact. Not a perfect memory. Tidal evolution has changed it, but enough survives to constrain the possibilities. Scientists also looked at what the Moon lacks. Compared with Earth, lunar material is depleted in many volatile elements. These are elements or compounds that move readily into a gas phase under sufficiently hot conditions. The Moon contains volatile material, including water in various reservoirs, so the old picture of an absolutely dry Moon has been abandoned. But its bulk composition still shows evidence of volatile depletion relative to Earth. Some isotope systems also carry signatures consistent with high-temperature processing. Potassium is one example. High-precision measurements found lunar rocks enriched in the heavier potassium isotope relative to terrestrial material and meteorites. The researchers argued that the result was consistent with incomplete condensation from a high-pressure silicate vapor after a very energetic moon-forming impact. That is exactly the sort of evidence scientists need when reconstructing a vanished environment. Nobody measured the temperature of the debris around Earth. Instead, researchers examined how elements separated according to volatility and how their isotopes were fractionated. The chemistry acts as a thermometer of sorts, a very complicated thermometer that takes several years of laboratory work to read. Other volatile elements tell similar but not identical stories. Recent samples have made this line of evidence even stronger. Material returned from the Moon's far side by the Chang'e. 6 mission allowed researchers to test whether volatile isotope effects previously measured mainly in near-side samples represented a moon-wide phenomenon or something caused by more local lunar geology. A 2025 study of sulfur isotopes in far-side samples concluded that the data supported a global volatile loss episode associated with lunar formation rather than simply later regional volcanic processing. This is a useful development because the Apollo mission sampled only the near side of the Moon, an extraordinary collection certainly, but still geographically limited. The Moon is a whole world. Imagine trying to reconstruct Earth's entire geology after visiting 6 locations in one hemisphere. You could learn a great deal. You would also have some questions. Samples from new locations help scientists determine which chemical signatures are truly global and which belong to particular lunar regions. Then there is the Moon's internal structure. Apollo astronauts left seismometers on the surface. These instruments recorded moonquakes, meteorite impacts, and artificial impacts, producing the first seismic network on another world. Seismic waves travel differently through materials with different densities, temperatures, and physical states. By studying their arrival times, scientists began reconstructing the lunar crust and mantle. Later analyses combined Apollo seismic measurements with spacecraft gravity data and lunar laser ranging, improving estimates of the Moon's deeper interior. Lunar laser ranging itself is one of the more delightful examples of leaving something useful behind. Apollo astronauts and Soviet robotic missions placed retroreflectors on the Moon. Observatories on Earth can fire laser pulses toward those reflectors and measure how long the light takes to return. Because the speed of light is known extremely precisely, the travel time provides an extraordinarily accurate Earth-Moon distance measurement. Over decades, those measurements have helped scientists study the Moon's orbit, rotation, tidal response, and internal structure. They have also provided evidence for a fluid lunar core through subtle effects on the Moon's rotational behaviour. So evidence for the ancient collision is not found only in rocks. It is also found in how the Moon wobbles, how it responds to tides, how seismic waves travel through it, how mass is distributed inside it, how it orbits Earth. Every measurement adds another requirement that an origin model has to satisfy. This is where computers enter the story. The basic giant impact idea predates modern high-resolution simulations. Scientists proposed large collisions as an explanation for lunar origin in the 1970s. But saying that a large body struck Earth is only the beginning. You need to know whether the physics actually works. Could such an impact place enough material into orbit? Would that material stay bound to Earth? Would it contain enough silicate? Too much iron? Would the collision leave Earth with the right mass? Would it make Earth spin too quickly? Would the debris have enough angular momentum to assemble into a moon? To answer these questions, researchers began running numerical simulations. One widely used technique is called smoothed particle hydrodynamics, or SPH. Instead of trying to calculate what every actual atom does, which would be a fairly unreasonable request even for a large supercomputer, the simulation divides the planets into many numerical particles. Each particle represents a portion of planetary material. The program tracks gravity, pressure, motion, density, internal energy, and other physical properties as the collision develops. At the beginning of a simulation, researchers construct a proto-Earth and an impactor. They choose their masses, their internal structures, their temperatures, the impact speed, the angle, sometimes their initial rotation. Then they allow physics to take over. Theia approaches. The worlds deform, material is thrown outward, a debris disk forms, or perhaps large clumps enter orbit directly. The simulation continues. Afterward, researchers measure the result. How much material remains in Earth? How much is orbiting? Where did it come from? How much iron is in the disk? What is the angular momentum? Does the result resemble the actual Earth-Moon system? The canonical 2001 Canup-Asphalt calculations were important because they identified a class of off-center impacts capable of producing an iron-poor moon with broadly appropriate mass and angular momentum when a smaller impactor struck Earth near the end of terrestrial accretion. But there was a problem. In those canonical simulations, much of the moon-forming material tends to come from Theia. Then Apollo chemistry says Earth and Moon are unusually similar. Physics seemed to want one thing, geochemistry seemed to want another. This tension did not kill the giant impact theory. It made the theory more interesting. Researchers proposed different solutions. Perhaps Theia formed very close to Earth, and therefore had a similar isotopic composition. Perhaps the impact produced stronger mixing. Perhaps the debris exchanged material with Earth's hot silicate atmosphere before the Moon completed its formation. Perhaps the proto-Earth was spinning very rapidly before impact. Perhaps the impact involved different masses. Perhaps the collision was much more energetic. Perhaps an extended vaporized structure called a synestia formed. Perhaps numerical resolution had been hiding important behavior. Each possibility makes predictions. Those predictions can be tested. That distinction is important. A good scientific model cannot survive merely by becoming more elaborate whenever evidence causes trouble. Eventually, it has to explain measurements better than competing models. The older alternatives for lunar origin had their own difficulties. One early proposal suggested that the Moon had been captured by Earth after forming independently elsewhere. Capture happens in the solar system. Small moons can be captured. But capturing something as massive as the Moon into its present kind of orbit requires losing an enormous amount of orbital energy without simply crashing into Earth or escaping again. The Earth-Moon isotopic similarity makes an unrelated origin harder to explain as well. Another proposal suggested that Earth and Moon formed together from the same local material, rather like a double planet system. That helps with chemical similarity. But it struggles with the Moon's small metallic core and other dynamical properties. A third idea proposed that the young Earth rotated so rapidly that material separated from it, sometimes associated historically with the notion that the Pacific Basin might mark where the Moon came from. Modern geology makes the Pacific part especially easy to reject. Ocean basins are products of plate tectonics and are vastly younger than the Moon, and simply spinning material off Earth creates major angular momentum problems. The giant impact did not win because it was the most exciting story, although admittedly a missing planet crashing into Earth does have an unfair advantage in that category. It became dominant because it could explain several awkward facts simultaneously: a large moon, a moon depleted in metal, an Earth-like silicate composition, evidence for high-temperature processing, the angular momentum of the Earth-Moon system, formation near the end of Earth's growth, a molten early moon. None of those alone proves Theia existed. Together, they create a much stronger case. This is how scientists reconstruct events they cannot observe directly. They search for explanations that survive multiple independent tests. A model that explains only the Moon's orbit but fails its chemistry is incomplete. A model that matches oxygen isotopes but produces a moon twice the correct mass has a problem. A model that creates the correct moon but leaves Earth rotating impossibly fast needs another mechanism to remove angular momentum. Every observation tightens the net, and as measurements become more precise, the net becomes tighter still. Some new evidence supports older versions of the giant impact. Some pushes scientists toward alternatives. Small oxygen isotope differences suggest Earth and Theia may not have been perfectly identical. Vanadium isotope measurements have been interpreted as supporting a canonical impact with substantial Theian material in the Moon. Tungsten models show how difficult certain versions of that same scenario can be if Earth and Theia evolve too differently before impact. Potassium points toward intense vaporization and condensation conditions. Seismic and laser ranging measurements confirm that the Moon has only a small metallic core. Impact simulations show that off-center planetary collisions can place iron-poor material into orbit with approximately the required angular momentum. None of this gives us a photograph of Theia. But science does not always require photographs. We know Earth's interior contains a core without seeing it directly. We know dinosaurs existed without watching one hatch. We know stars produce energy through nuclear reactions without placing a thermometer inside the sun. Evidence can preserve an event long after the event itself is inaccessible. Theia's evidence is simply distributed across an unusually large crime scene. Part of it is on the Moon, part is inside Earth, part is encoded in orbital motion, part exists in computer models showing which collisions are physically possible, and every year, instruments become better at reading what remains. Mass spectrometers measure isotope differences that earlier laboratories could not resolve. Spacecraft map lunar gravity more accurately. New sample return missions bring material from regions never sampled before. Old Apollo seismic records are reanalyzed with techniques and computing power that did not exist when the instruments were operating. A dataset can be decades old and still reveal something new when scientists ask a better question. That may be one of the most remarkable parts of this investigation. The moon-forming collision happened roughly 4.5 billion years ago, but our reconstruction of it is still changing. Theia is becoming clearer long after Theia ceased to exist. not perfectly clear. We still do not know its exact mass. We do not know its precise orbit. We do not know exactly how much of the Moon came from Theia. We do not know whether the collision followed the traditional Mars-sized impact scenario, a higher energy alternative, or some variation that future simulations will reveal more convincingly. Science has not reached the point where we can replay the event second by second. What it has done is narrow the range. A completely unrelated captured moon is difficult to reconcile with the evidence. A moon simply spun intact from modern Earth does not work. A quiet origin does not explain the high-temperature chemical signatures very well. A giant collision between differentiated planetary bodies fits a remarkable number of observations, even though the exact collision remains under debate. And once scientists recognized that an impact could explain the Moon, another question became unavoidable. The Moon was not merely something created beside Earth. The Moon began changing Earth almost as soon as it existed. That does not mean the collision suddenly turned the young planet to the comfortable world we know today. Earth still had billions of years of geological, atmospheric and biological change ahead of it. The Moon did not create the oceans, invent plate tectonics, or personally arrange for someone to make tea several billion years later. What it did was establish a gravitational relationship that has been operating ever since. Earth pulls on the Moon pulls on Earth. Both bodies deform slightly because of that attraction. Energy is dissipated. Angular momentum is transferred. Earth's rotation changes. The Moon's orbit changes. And once liquid oceans existed on Earth's surface, the Moon became the strongest external influence on the tides we see today. The familiar version of tides usually begins at the beach. You stand near the sea for several hours and notice that the water level changes. At one time, rocks near the shore are exposed. Later, they disappear beneath the water. Harbours rise and fall. Mudflats appear and vanish. Boats that were floating comfortably can find themselves sitting at an angle if their owners have been particularly optimistic about the tide table. The main reason for this rhythm is the Moon's gravity. The Moon attracts the near side of Earth more strongly than Earth's centre, and it attracts the far side slightly less strongly. The result is a differential gravitational effect that helps produce two broad tidal bulges. Earth rotates beneath this changing distribution of ocean water, giving most coastlines a repeating cycle of high and low tides, although the actual timing and height of tides depend strongly on coastline shape, ocean depth, continents, and local geography. The Sun also produces tides, but because the Moon is much closer to Earth, the lunar contribution is the stronger one. The tides themselves are not simply water being lifted directly toward the Moon like someone pulling a tablecloth upward. Real ocean tides are waves moving through complicated ocean basins. Continents get in the way. Seafloors have ridges and trenches. Water moves through narrow channels. Local resonance can amplify or reduce the result. That is why some coastlines experience enormous tidal ranges, while others see much smaller changes. The Moon supplies the main astronomical forcing, but Earth decides how messy the local response will be. The early Earth would have been even more complicated. The continents did not have their modern arrangement. The oceans, once established, had different shapes and depths. The Moon was closer. Earth rotated faster. Every one of those differences changes tidal behaviour, so we should be cautious, with the popular image of the young Earth experiencing one simple, universally enormous tide sweeping around the planet. Early lunar tides were stronger because the Moon was closer, but the actual ocean response would have depended on the changing geography and physical state of Earth. There is also a more important consequence hidden inside those tides. They act like a brake on Earth's rotation. Not a sudden break. Nobody pressed a pedal and changed a 6-hour day into a 24-hour day before lunch. The process works gradually through tidal friction and the transfer of angular momentum between Earth and the Moon. Earth rotates much faster than the Moon travels around it. Because of that fast rotation, Earth's tidal response is carried slightly ahead of the line directly connecting Earth and Moon. The gravitational attraction between the Moon and this displaced tidal bulge gives the Moon a small forward pull in its orbit. That adds orbital angular momentum to the Moon. The Moon responds by moving into a slightly more distant orbit. Earth, meanwhile, loses rotational angular momentum. Its spin slows. The day becomes longer. It's a very slow exchange, but it has had an enormous amount of time to work. The Moon is still moving away today. Lunar laser ranging using reflectors placed on the Moon during the Apollo era measures the present recession at about 3.8 centimeters per year. At the same time, the long-term tidal effect contributes to a gradual slowing of Earth's rotation, commonly expressed as an increase in day length of roughly milliseconds per century, although Earth's measured rotation also varies because of interactions involving the atmosphere, oceans, mantle, and liquid core. 3.8 centimeters does not sound dramatic. It is roughly the sort of distance you might ignore when moving a chair, but apply a process over hundreds of millions and billions of years, and small annual changes become very large ones. The Moon used to be much closer. Earth used to rotate much faster. This is not simply something scientists calculate from theory. Ancient rocks preserve clues. Some sedimentary rocks contain repeating layers produced by tidal cycles. These are called tidal rhythmites. Tides move sediment. Different parts of the lunar month produce different tidal strengths. If those variations become recorded as repeating layers and the deposits survive, geologists can sometimes use the pattern to estimate how many days occurred in an ancient month or year. From there, they can infer something about Earth's rotation and the Moon's orbital distance at the time the sediments formed. A set of roughly 620 million-year-old rhythmites in South Australia has been interpreted as recording about 400 days in a year and a day length of roughly 21.9 hours. The year itself was not dramatically shorter. Earth still needed approximately the same amount of time to orbit the Sun. The difference was that Earth rotated more times during that orbit. Shorter days mean more days can fit inside a year. Go farther back and the uncertainty becomes larger, but geological evidence still points toward faster rotation. Some Precambrian records have been used to infer even shorter days, and a 2023 analysis proposed that Earth's day may have remained close to 19 hours for a long interval during the Middle Proterozoic, because atmospheric and oceanic tidal torques temporarily balanced one another. That specific history remains an area of continuing research, which is a useful reminder that Earth's rotation did not necessarily slow at one smooth, constant rate. The modern recession rate cannot simply be multiplied backward for 4.5 billion years. Do that, and you quickly produce nonsense. Tidal dissipation changes as oceans and continents change. A shallow sea can dissipate tidal energy differently from a deep ocean. Continents move, ocean basins open and close, resonances appear and disappear. Earth's atmosphere also produces thermal tides that can influence rotation. The strength of the entire braking process has therefore varied greatly through geological time. This is why the present Moon cannot simply be reversed at 3.8 centimeters per year like a video. The history has to be reconstructed. Ancient sedimentary cycles, fossil growth patterns, orbital calculations, tidal models, lunar laser measurements, all of them contribute, and the result is a Moon that began much closer to Earth, then migrated outward while Earth's rotation slowed. Theia's collision therefore changed something as ordinary as the length of a day. Not directly to 24 hours, that took an enormous amount of later tidal evolution. But without the Moon, the history of Earth's rotation would have been very different. The Sun also raises tides on Earth and can change planetary rotation over long periods, so a moonless Earth would not simply keep its original spin forever. But the large Moon introduced an especially strong tidal partner. The planet has been giving rotational angular momentum to that partner ever since. There is another effect that is often described in much stronger terms than the science really allows: Earth's axial tilt. Our planet does not rotate with its axis perfectly upright relative to its orbit around the Sun. It is tilted by about 23.4 degrees today. That tilt is the main reason we have seasons. During part of Earth's orbit, the northern hemisphere leans more toward the sun and receives more direct sunlight. 6 months later, the southern hemisphere does. Earth's tilt is not perfectly fixed. It changes gradually. Over familiar geological timescales, Earth's obliquity varies within a relatively narrow range, contributing to long-term climate cycles. The Moon affects that stability. A classic 1993 calculation found that the Moon increases the precession rate of Earth's spin axis in a way that helps keep the present planet away from strong chaotic resonances with the gravitational perturbations of the other planets. In those calculations, removing the Moon allowed Earth's obliquity to enter a much broader chaotic range, potentially producing very large variations. That result produced a very popular statement. Without the Moon, Earth's axis would tumble wildly. The climate would become catastrophic. Complex life might never exist. It is an excellent sentence for documentaries. It is also more certain than the science allows. Later, numerical work looked at hypothetical moonless Earths over very long periods and found a more complicated picture. Those simulations still showed substantially greater obliquity variation without the Moon, but many cases remained within a more limited range for hundreds of millions of years rather than wandering freely from nearly 0 to almost 90 degrees. The authors concluded that a large moon is not necessarily required for an Earth-like planet to maintain a reasonably constrained axial tilt over timescales relevant to biological evolution. So the careful version is this. The Moon does stabilize Earth's spin axis behavior. It helps keep the actual Earth's obliquity within the relatively narrow variations we experience. Without it, Earth's axial tilt would probably vary more. Exactly how much more depends on Earth's rotation rate, the initial tilt, and the long-term gravitational behavior of the rest of the solar system. That is less dramatic than saying the Moon heroically prevents Earth from falling over. It also has the advantage of being more accurate. An Earth does not need help falling over in the ordinary sense anyway. There is no universal up direction in space for the planet to fall toward. What matters is the angle between Earth's spin axis and its orbital plane. Large changes in that angle would redistribute sunlight between latitudes and alter the pattern and strength of seasons, with potentially major climatic consequences. The Moon has therefore influenced Earth's climate history indirectly through rotational dynamics, although it would be a mistake to treat it as Earth's climate control system. Climate depends on the atmosphere, ocean circulation, continental positions, greenhouse gases, ice, solar luminosity, volcanism, life, orbital variations. The Moon is one contributor to the long-term astronomical framework in which all of those processes operate, a large contributor in some respects, not the only one. Its most visible effect remains the tides. Once oceans existed, tidal motion repeatedly moved water across shorelines. That created coastal environments that change predictably between submerged and exposed conditions. Tidal currents moved nutrients and sediments. Shallow marine systems experienced regular cycles connected to the Moon's orbit. Life eventually evolved within a planet where lunar rhythms were simply part of the environment. It is tempting to take the next step and say tides were necessary for life to move onto land, or that the Moon was required for life to begin. Those ideas have been suggested in various forms, but they are not established conclusions. The origin of life remains unresolved. Scientists do not know whether the first life emerged in shallow pools, hydrothermal systems, mineral surfaces, or some other environment, and there is no evidence that a planet must possess a large moon before biology can appear. So Theia should not receive credit for inventing life. That would be an impressive achievement even by planetary collision standards. What can be said is more modest. The Moon created strong, persistent tidal forcing that became one environmental feature of Earth's oceans and coastlines. Life evolved under those conditions. Many organisms later evolved biological rhythms connected to lunar and tidal cycles, but that is different from proving that the Moon was necessary for life itself. Earth would still have tides without the moon. The sun produces them. They would simply be considerably weaker than the combined tidal environment of the present Earth-Moon system. NASA identifies the moon as the dominant influence on modern terrestrial tides because of its proximity, while solar gravity modifies those tides to produce spring and neap cycles. The relationship between Earth and Moon also works in the other direction. Earth raises tides on the Moon. The Moon is solid, but solid rock can deform. The displacement is much smaller than an ocean tide, yet laser ranging can detect changes in the lunar surface produced by Earth's tidal pull. NASA notes that Earth's gravity can deform the Moon by roughly 10 to 15 centimeters in the relevant tidal response. Over the Moon's early history, tidal effects were much stronger because the two bodies were closer. Those forces altered the Moon's rotation until it became tidally locked. That is why the same lunar hemisphere generally faces Earth today. Its rotation period and orbital period became synchronized, so the impact did not simply produce a moon and then allow the two bodies to ignore one another. Earth changed the Moon. The Moon changed Earth. Their present behavior is the result of billions of years of mutual gravitational adjustment. Even the Moon's current orbit preserves signs of that complicated history. The lunar orbital plane is tilted by about 5 degrees relative to Earth's orbital plane around the Sun, and explaining how that inclination developed from a moon expected to form near Earth's equatorial plane has been a long-standing problem in lunar dynamics. Models invoke processes including tidal evolution, resonances, high early lunar inclinations, and encounters with leftover planetesimals. This matters because it shows that the Earth-Moon system did not slide smoothly from the impact into its current arrangement. There were dynamical transitions. The Moon crossed resonances as it moved outward. Its orbital inclination changed. Earth's tilt and rotation evolved. The Sun's gravitational influence became increasingly important as lunar distance increased. Some models propose surprisingly complicated periods in which the young Moon occupied a highly inclined orbit before tides gradually moved the system toward its modern configuration. The neat diagram we see today is the end result of a very long adjustment. Earth in the center, Moon moving around it. 24-hour day, month lasting about 27 days relative to the stars. Average lunar distance around 384,000 kilometers. An axial tilt a little above 23 degrees. None of those values had to be exactly what they are now. Immediately after Theia struck, they evolved. The day changed, the month changed, the distance changed, the orientation changed, and the evolution has not stopped. The Moon is still receding. Earth's rotation is still affected by tides. The shapes of ocean basins continue changing as plate tectonics rearranges continents, which means the efficiency of tidal dissipation also changes over geological time. There is something useful about considering the collision from this perspective. We normally focus on the dramatic moment. Theia reaches Earth, the worlds collide, rock is vaporized, debris enters orbit. The Moon forms. That sounds like the main event. But from Earth's point of view, the aftermath lasted far longer than the impact. The physical collision may have destroyed Theia as an independent planet within hours. The gravitational consequences have been operating for billions of years. Theia changed Earth by changing what Earth was connected to. Before the collision, there was a young planet moving around the Sun. Afterward, there was a planet with an unusually large satellite. That satellite began taking angular momentum from Earth's rotation through tides. It began moving outward. It influenced the stability of Earth's spin axis. Once oceans formed, its gravity generated strong repeating tides. All of those processes continued while the surface evolved from a hot post-impact environment into a planet with oceans, continents, atmosphere, and eventually life. The Moon was present for nearly all of that later history. Dinosaurs saw it. The earliest animals lived beneath its tides. Long before animals existed, microbial ecosystems experienced days and tidal cycles shorter than our own. The first forests grew on an Earth whose moon was somewhat closer than it is now. Every human civilization has lived during only the latest tiny fraction of a relationship that was already ancient before multicellular life became common. And our experience makes the modern arrangement feel permanent. 24 hours feels like the natural length of a day. The moon's apparent size feels normal. Its position in the sky feels normal. High and low tides feel normal. But they are only the current state of a changing system. Travel far enough into Earth's past and the day becomes shorter. The moon becomes closer. Its orbital period changes. Tidal patterns differ. Travel far enough into the future and the opposite trend continues, although predicting the exact details becomes increasingly complicated as the Sun and Earth themselves evolve. The moon we see tonight is therefore not sitting at the distance where it began. Earth is not spinning at the speed it had after the collision. The system has spent billions of years exchanging energy and angular momentum, with every tide contributing a tiny part of the change, and all of that traces back to a planet that no longer appears in any map of the solar system. If Theia had missed Earth, there may have been no large moon produced by this event. Earth's rotational history would have been different. Its tidal history would have been different. Its axial behavior would have been different. How those differences would have changed geology, climate, and life cannot be reconstructed with certainty, because there is no second Earth available where Theia politely flew past for comparison. There is only this Earth, the one that was hit, the one that incorporated part of Theia, the one whose moon formed from the aftermath. And that makes the final part of Theia's story slightly stranger than simply saying the lost planet created our satellite. Theia may still be influencing ordinary events every day. A tide coming in along a coast, a day that lasts 24 hours rather than the much shorter days of ancient Earth. A moon slowly moving farther away. A spin axis whose behavior is altered by the gravitational presence of that moon. Those are not temporary remnants of the impact. They are features of the system the impact created, and beneath all of them sits one awkward fact that is easy to overlook. Theia is not entirely gone. Some of its material may be in the moon, some may be mixed through Earth, some may have joined Earth's core. Perhaps large remnants of its mantle are still preserved near the core mantle boundary, which means that after following the collision from a vanished planetary embryo to tides, rotation, and the moon above us, there is still one last question worth asking. How much of the world created by Theia are we actually living on now? The answer is that we may be living on more of Theia than we can currently identify, not because scientists have found a neat layer of alien rock underneath the crust, and certainly not because half of Earth secretly belongs to another planet in a way that could be marked on a map. Theia's legacy is much less tidy than that. After the collision, its material was divided, mixed, buried, melted and incorporated into the Earth-Moon system. Some of it almost certainly became part of the Moon. Much of it became part of Earth. Its metallic core probably joined Earth's growing core. Its rocky mantle was distributed between Earth and the orbiting debris, and some portion may have escaped the system entirely. After more than 4 billion years of geological activity, most of those materials can no longer be separated simply by looking at them. A piece of modern Earth does not come with a tag saying, "Formerly Theia," neither does a lunar rock. Scientists have to search for differences in chemistry, isotopes, density, and structure that might preserve information from before the collision. And that brings us back to the most important thing about Theia. It disappeared as a world, but it may not have disappeared as material. The distinction is easy to miss because we tend to think of planets as permanent objects. Earth is Earth. Mars is Mars. Venus is Venus. They have names, positions, maps, and recognizable appearances. But planets are collections of matter held together by gravity. Change where that matter goes, and the object itself can cease to exist, even while almost all of its ingredients remain somewhere else. Theia lost its separate orbit. Its core no longer sat inside its own mantle. Its gravity no longer held a planet together. Its surface, whatever that surface looked like, was destroyed. Its independent history ended, but the matter survived. Some of it may be hundreds of thousands of kilometers above us. Some may be thousands of kilometers below us. That is probably the most concrete way to understand what Theia left behind. Look upward, and there is the moon. Look downward, and there is Earth. Both may contain material from the same lost planet. The moon is the easier part to see. Even without a telescope, it is large enough to show shape and phase. With binoculars, the broad dark maria become obvious. With a modest telescope, crater walls, mountain shadows, and bright highlands appear. None of those surface features existed immediately after the collision. They developed later. But the material beneath them came from the aftermath of that event. The moon is therefore not simply a witness to Theia. It is one of the products made from Theia and the Proto-Earth together. Exactly how much came from each body is still debated. Some collision models produce a moon made largely from Theian mantle. Others produce more material from the Proto-Earth. High-energy scenarios can mix the two bodies more thoroughly. Different assumptions about Theia's mass, speed, angle, and composition change the proportions. This uncertainty matters, but it does not erase the central conclusion. The moon formed because a major collision placed rocky material into orbit around the young Earth. Without that event, the moon we know would not exist. The ancient planet therefore remains visible in the most ordinary way possible. It rises, it sets, it goes through phases, it produces eclipses. Its gravity contributes to the tides. People photograph it with their phones. Children draw it in the corner of pictures. Astronauts have walked on it. All of that traces back to a time when another planetary body occupied the inner solar system and eventually collided with Earth. The second part of Theia's legacy is harder to observe because it may be inside the planet beneath us. Earth is not simply the proto-Earth after surviving a collision. Its mass and composition were changed by the impact. Theia delivered material. Its metallic core likely contributed to Earth's core. Its mantle material entered Earth's silicate interior. Some of that material may have mixed thoroughly. Some may have remained less completely mixed. The possibility that large pieces of Theia's mantle survived deep inside Earth is especially interesting because it gives scientists a potential place to look for the impactor without leaving the planet. The enormous low-velocity regions near the base of Earth's mantle remain one candidate. The structures beneath Africa and the Pacific are real. Their interpretation is still debated. They may contain material produced entirely by Earth's own internal history. They may contain material associated with ancient mantle differentiation, or, as some impact models suggest, they may include dense pieces of Theia that survived the collision and sank toward the core mantle boundary. At the moment, scientists cannot simply take a sample. The core mantle boundary lies almost 3,000 kilometers beneath Earth's surface. The deepest drilling humans have ever achieved reached only a tiny fraction of that distance. Our direct access to the deep mantle is extremely limited, so once again, scientists have to work indirectly. Earthquakes provide information about structure. Laboratory experiments show how minerals behave at enormous pressures and temperatures. Computer models test whether dense impactor material could survive and sink. Geochemical measurements look for unusual signatures in volcanic rocks that may have originated from very deep mantle sources. Each method gives part of the picture. None has yet produced a rock that can be held up and identified unquestionably as a surviving piece of Theia. Perhaps that will change. Future measurements may show that the large, deep mantle structures are connected to the moon-forming impact, or they may reveal a different origin entirely. Either result would be useful. Science does not require Theia to remain hidden inside Earth for the giant impact idea to work. The possibility is exciting because it would preserve an unusually direct remnant of the lost world. But Theia's broader legacy does not depend on it. We already have the moon. We already have Earth's altered composition. We already have a planet and satellite whose chemistry and motion point back toward an enormous early collision, and the consequences of that collision did not remain confined to the first few days after impact. They continued changing Earth for billions of years. The moon began moving outward. Earth's rotation slowed. The length of the day increased. The tides changed as the distance between the two worlds increased and Earth's oceans and continents evolved. The moon became tidally locked so that one hemisphere remained generally facing Earth. Its interior cooled, its magma ocean crystallized, its surface accumulated craters. Earth cooled too. A new crust formed. Atmospheres developed and changed. Liquid water became stable at the surface. Oceans appeared. Continents grew and moved. Life emerged. Through nearly all of that history, the moon was already there. It did not remain at its original distance. It didn't have its modern appearance. But the gravitational partnership created by the impact had become a permanent part of Earth's environment. That makes Theia different from most lost objects in the early solar system. There were probably many planetary embryos that no longer exist. Some were swallowed by larger planets. Some collided with each other. Some may have fallen into the sun. Some may have been thrown out of the solar system. Their names are unknown because nobody had any reason to give them names. Theia is remembered because its disappearance produced something enormous and obvious. The moon. If Theia had struck Venus instead, perhaps Venus would have a very different satellite system today. If it had missed Earth and remained stable, the inner solar system might have contained another planet. If it had been ejected, it could have wandered into interstellar space. If the collision angle had been slightly different, the outcome might not have produced a large moon at all. A more direct impact could have merged the two bodies with much less material left in orbit. A faster encounter might have allowed more debris to escape. A different mass ratio could have produced another arrangement entirely. The moon exists because the conditions of the collision fell into a range that allowed orbiting material to survive and gather. This does not mean the event was somehow arranged for Earth. There was no intention involved. Planetary formation produces collisions naturally. Some create moons, some destroy them. Some merge worlds, some strip away atmospheres. We happen to live on one of the outcomes. That is worth remembering, because it changes the way Earth's history looks. Our planet is often described as though it gradually developed from a young rocky sphere into the modern Earth. That is true in a broad sense, but gradual development was repeatedly interrupted by large events. Earth grew through collisions, its interior differentiated, its surface melted more than once. Material was added, material was lost. The moon-forming impact was probably among the most important of those events, because it altered Earth at planetary scale and created a second large body in the process. Modern Earth is therefore not simply an untouched survivor from the beginning of the solar system. It is a reconstructed world. The planet has been rebuilt so many times geologically that almost none of its earlier surface remains. The continents beneath us are much younger than Earth itself. Oceanic crust is younger still. Plate tectonics continually destroys and creates surface material. Mountain ranges rise and erode. Volcanoes bring new material upward. Sediments are buried. Nothing at Earth's surface stays ancient for very long compared with the age of the planet. The moon keeps an older record. Its lack of active plate tectonics means ancient terrains can remain visible for billions of years. That is one reason it has become so important for understanding not only its own history, but also the history of the early inner solar system. Large impact basins preserve evidence from periods Earth has almost completely erased. Ancient lunar crust records the crystallization of an early magma ocean. Isotopes in lunar samples preserve clues about high-temperature processes during formation. Every mission that returns new material adds another piece, and future missions could bring back samples from places that may preserve deeper or less altered material. The lunar far side is particularly valuable because it differs from the near side in crustal thickness, volcanic history, and impact structure. The South Polar region is interesting for entirely different reasons, including permanently shadowed areas where volatile materials can accumulate. Deep impact basins may expose material from beneath the crust. Each location provides another opportunity to ask the same old question with better evidence. What exactly was the moon made from? If scientists can identify differences between material derived from the proto-Earth and material derived from Theia, they may eventually reconstruct the impactor's chemistry with much greater confidence. Perhaps we will learn where in the inner solar system Theia formed. Perhaps we will estimate how much iron its mantle contained. Perhaps its oxygen isotope composition will become clearer. Perhaps future simulations will converge on a narrower range of possible masses and impact angles. We may never know what its surface looked like. We may never know whether it had already developed a stable crust. There will never be a map of Thean mountains, but we may eventually know enough about its composition and history to describe it as more than simply the body that hit Earth. That would be an unusual scientific achievement. Reconstructing a planet after the planet itself has been gone for more than 4 billion years. The evidence is already surprisingly detailed. Scientists can estimate when the solar system formed. They can date ancient lunar minerals. They can compare Earth and Moon isotopes to tiny fractions. They can model the behavior of molten silicate at pressures no human could survive. They can simulate a collision involving bodies thousands of kilometers across. They can bounce lasers off reflectors on the Moon and measure its changing orbit with extraordinary precision. They can use earthquakes to map structures near Earth's core. All of these methods investigate different pieces of the same event, and yet there is no final photograph. No single measurement says everything. The reconstruction works because independent lines of evidence overlap. The Moon's small metallic core fits an origin from mantle-rich debris. Its early magma ocean fits an extremely hot formation. Its volatile depletion points toward high-temperature processing. Its isotopic similarity to Earth constrains the composition of Theia and the amount of mixing. The angular momentum of the Earth-Moon system constrains the geometry of the collision. Earth's deep interior may contain additional clues. Put these observations together, and a lost planetary body becomes difficult to avoid. The details remain adjustable. The impactor remains partly unknown. But something large struck the proto-Earth. That is why Theia has become more than a convenient name. It represents a missing member of the early solar system, whose existence can be inferred from what survived. There is also something slightly amusing about the fact that humans spent most of history looking directly at one of the biggest pieces of evidence without understanding what it meant. The Moon was always there. People noticed its phases thousands of years ago. They measured months with it. They named gods after it. They wrote poems about it. They worried about eclipses. They used its light at night. Nobody could know that its origin might involve another planet because the evidence required modern geology, chemistry, astronomy, and physics. Even after telescopes revealed mountains and craters on the Moon, its formation remained uncertain. Only when lunar samples returned to Earth could scientists begin comparing the two worlds directly. The mystery became solvable because we went there, and the solution remains unfinished because science rarely provides a perfectly neat ending. The giant impact framework is strong. The exact identity of Theia is not. We have a name for the missing planet, but not a photograph. We have models of its mass, but not one universally accepted value. We have ideas about where it formed, but not a known original orbit. We have candidate remnants inside Earth, but no direct sample from them. We have lunar material that probably contains Theia, but separating it from proto-Earth material is extremely difficult. That uncertainty should not make the story less interesting. It makes it more realistic. Theia is not a fictional planet inserted into a gap. It is a scientific reconstruction. Every improvement in measurement can change the reconstruction. The picture becomes sharper by degrees, and some questions may remain open for a very long time. Perhaps the most interesting of those questions is whether the Moon was essential to the Earth we eventually became. We have already seen that some popular claims go too far. There is no good reason to say that life could not exist without a large moon. We cannot say that complex organisms require one. We cannot say Earth would have become uninhabitable if Theia had missed. There is no second version of Earth available for comparison. but we can say the planet would have evolved differently. Its rotation history would change, its tidal environment would change, its axial dynamics would change, its early thermal and chemical history would change because the giant impact itself would be absent or replaced by some other event. Those differences could become important over geological time. The Earth we know is therefore one possible result among many. We live on the version that met Theia, and every clear night gives us a reminder. The moon now looks calm because we are seeing it long after its most violent period. From Earth, it moves slowly across the sky. Its light is reflected sunlight. Its phases follow a predictable cycle. Nothing about that appearance suggests molten debris colliding moonlets or a planetary mantle being pulled apart. The violence has been over for billions of years. What remains is stable enough that humans once used the moon to define calendars and now use it as destination for spacecraft. That contrast is one of the easiest ways to understand deep time. The same object can have completely different roles at different stages of its history. The newborn moon was a hot body assembling from impact debris. Later, it became a cooling volcanic world, then a heavily cratered satellite. Much later, it became an object watched by living things on Earth. Eventually, one of those species built rockets and returned pieces of it to the planet, from which much of its material may originally have come. A lunar rock carried to Earth by an astronaut may therefore have completed a very long journey. Part of its material may have started in the proto-Earth. The impact threw it into orbit. It became part of the moon. It remained there for billions of years. Then humans picked it up and brought it back. Other atoms in the same rock may have begun inside Theia. They travelled through an even stranger route, a separate planet, a collision, an orbiting debris field, a molten moon, a solid crust, billions of years on the lunar surface, then a spacecraft, then a laboratory on Earth. It is difficult to ask matter for a more complicated travel itinerary. And here we are now, long after all of it. Earth rotates beneath us. The moon moves around it. The distance between them increases by a tiny amount each year. Tides continue transferring energy. The continents continue moving. Earth's interior continues cooling. Whatever Theian material became part of our planet continues participating in that evolution. The collision is finished, its consequences are not. So, think back to the question from the beginning. Where are you listening from tonight? Perhaps you're somewhere with the moon visible outside. Perhaps you're in a city where buildings hide most of the sky. Perhaps clouds have covered it. Maybe the moon has not risen yet, or perhaps it has already set. Wherever you are, you're listening from the same place in one important sense. You're on the surviving world, the larger body that remained after two young planets met, and somewhere above you is the companion produced by that meeting. We started with a planet that no longer exists, a world with no surviving name from its own time, no surface we can visit, and no orbit we can plot today. We followed it through a crowded young solar system, into a collision with the proto-Earth, through a disk of hot debris, and into the formation of the moon. We found that disappearance is not quite the right word. Theia was broken apart. Its material changed ownership. Its core likely became part of Earth. Its mantle contributed to Earth, the moon, or both. Some pieces may still be deep below us, and the most obvious result remains overhead. If you've enjoyed this journey through the early solar system, you can give the video a like and subscribe to Science for Sleep. It helps this quiet corner of science reach other people who may also enjoy learning what happened when a missing planet collided with Earth, preferably while being safely several billion years late to the event. And if you're still awake, perhaps have one last look toward the moon when you get the chance. It is easy to think of it as something separate from Earth, a distant grey sphere, a companion travelling beside us. But its history is tied directly to our own. Earth and Moon are two surviving parts of an event that involved another world. Theia no longer circles the Sun. It has no place in the modern list of planets. But it helped determine what Earth became, and it left behind something large enough for every generation of humans to see. So wherever you're listening from, and whatever time it is in your little part of Earth, the moon above us carries evidence of a much younger solar system, when planets were still forming, orbits were still changing, and one lost world came close enough to Earth that the two would never truly be separate again. Sleep well, fellow traveller, and if moonlight reaches your window tonight, remember where at least part of that moon may have come from.